Again, thank you everyone for attending today and yesterday. Yesterday was great, a lot of great implementation discussions. Again, we'll continue on that flow through NRRA. And with today, it's really looking at the teams and what the teams are doing and kind of what their direction, their future direction. And then we'll follow it up with kind of a summary myself before we go on the tour. The tour this afternoon will be at MnRoad, and again, a couple people asked me where to go when you get to MnRoad. Well, once you go to MnRoad, you'll see where people are at, put it that way. It's not that big, you drive the driveway, and there it is. So with that, I guess we start out today with the ICT team. I'll let Kyle take it from here.
All right.
Thanks, Kyle.
Yes.
You can wander.
All right. I won't wander. I'm not a wanderer. So I was talking to Professor Nazarian just earlier here, and I thought I was going to steal the way that he put the ICT team, but then I figured you guys would know it's way too eloquent for it to come from me. So, but the way he put it is that with the ICT team, we're kind of an oddball. That's my words. And the way he put it is that really the other four teams are kind of our clients. So I think this is a good opportunity for us when we all come together to give you guys a bit of an update on what we've been doing, because when we talk every month, it's a bunch of ICT people, you know, non-destructive evaluation and all that kind of stuff. But really these tools are supposed to be supporting the other groups. So I think we'll probably make a concerted effort moving forward if we have a presentation pretty much every month to try to get whatever specific team it's related to invited, so they can kind of hear about what the latest and greatest is and help give us direction and things like that. So with that, I was just going to give a little bit of an update on some of the presentations we've had, and one of them was presented yesterday, North Dakota, giving an update on some of the stuff they're doing with asphalt paving and DPS and paver mounted thermal profile and all that kind of stuff. And you all heard that yesterday. We have a couple projects coming down the pipe. The first one is it's kind of an NDT methods evaluation, and these sort of things have been done in the past, but as you all know, the technology it's evolving all the time. So the idea here is to kind of get a good, hopefully statistical measure of, you know, probability of detection, accuracy, those sort of things for the various tools that are available today. And the goal with this one, once it gets going, is let's try to prioritize what are the higher priority problems that we're trying to solve, and then figure out, you know, what's a realistic piece of information we could get from an accuracy point of view to use these various tools or NDT methods to solve them. And again, there's some candidate methods that Professor Nazarian listed out, but we're going to be looking at all the latest and greatest tools, and then figuring out a way to put it to the test with ground truth. And we have some ideas for what we can do out at MnRoad, but then also live projects too, to get some ground truth data and evaluate where these technologies are. Another exciting one, which I think is just went through the financial offices. I think there was a fight between Texas and Minnesota about sovereignty. Nothing, no big deal. But they got that figured out, and I think actually Texas is a part of Minnesota now as a part of this thing. Okay, so I don't think they'd have any problem with that down there. So anyway, with this project, again, looking at traffic speed deflectometer application, and again, the goal is to get a tool and guidelines for best use of the technology. I thought Amanda put it pretty good yesterday with her story about the contractor of all you're doing is creating best practices and ensuring quality or something like that. Well, that's the goal with all these technologies. And he'll do, all these kind of fancy evaluations to figure out kind of what are the boundary conditions, where's the best use of this technology and all that kind of stuff. We had a nice presentation from Iowa DOT, their e-construction person, Matthew Miller, went over a lot of different initiatives that they're doing a pretty impressive job with there. E-ticketing was a big one, and again, just figuring out what's working, what's not working, all those kind of things in Iowa. And I just wanted to highlight one thing from that presentation. Amy mentioned from North Dakota issues with internet connection. So we had to get the corrected GPS a lot of times through an internet connection, and all these intelligent technologies aren't that intelligent if they don't have a Wi-Fi signal. So they've done some pilot projects with these suitcases, and Rebecca Embacher brought that to our construction unit, and it looks like we're going to try those things out on a few projects this coming construction season. Right, Curt? We're going to try those suitcases out? Sure. Yeah. So, and then, so maybe that's something North Dakota wants to try out too, but just little things like that, when you present, what people are doing every month, it's good to learn from each other and see if we can solve some problems. George Chang gave a presentation related to a project he did for both federal highway and then one through the NRRA, and again related to intelligent compaction measurement values. But then, so he went into all the details, but then, also kind of just simple use, identifying weak areas with intelligent compaction on foundation, and how it might help for contractors trying to do a good job out there. And then lastly, a presentation from Ken Mazer, and this is a collaboration with Tom Burnham and the Rigid group using 3D GPR for analysis of concrete pavement evaluation, and this is trying to move towards automation for some of the more systematic evaluations like dowel misalignment and things of that nature. So with that, we wanted to highlight one of our completed projects. So Subu is going to come up here and talk about asphalt real-time smoothness. So let's welcome Subu.
Thank you, Curt. So my name is Subu. I'm with the Transtec group, and I'm here to talk about the beautifully named ARTS project. It's asphalt real-time smoothness. I'm presenting this on behalf of Dr. George Chang, who couldn't be here with us today because he's attending a different conference. I'm also told that the choice to attend the other conference instead of this one had nothing to do with the fact that the other conference is in Florida. All right, so let's get started. So real-time smoothness is a technique that they have used for like concrete pavers to measure the smoothness of the freshly placed concrete behind the paver, and to tweak the paver operations so that they can maintain the roughness of the freshly placed concrete below a certain threshold, right? So this project is a counterpart to that we are trying to do the same real-time smoothness measurement, but behind the paver straight of an asphalt paver, and be able to isolate the roughness caused by the paver operation from the roughness caused by the compaction operation. The goal here is that by isolating the roughness caused by the paver operation, we can tweak the paver operation to reduce the roughness, thereby ending with the overall smooth project. All right. So on this slide is a layout of the ARTS prototype sensor. The reason we say it's a prototype is because it's not fully developed, is my understanding. So it's basically a laser measurement device. Like it has 3 lasers. On the top left, you have the green items are the lasers themselves. And on the top right is the real life version of them. The 3 rectangular boxes at the bottom are the laser sensors. They measure the distance from the laser sensor to the surface of the freshly placed asphalt using a triangulation method. And the bottom here shows you the same laser from the, like a photograph of it from the bottom. It shows you the laser dot there as well. So there were 2 of these sensors that were mounted on one on each wheel path, about 6 feet apart from each other and 4 feet behind the screen. Essentially, the entire setup is mounted to the back of the screen, so the setup moves with any movement of the screen itself. There is also a distance measuring instrument, the DMI, that measures the the distance traveled as the surface of the asphalt is being profiled. One aspect that is different from a concrete or RTS system would be the fact that, asphalt is very hot and electronics does not like hot. So we have 2 cooling chimneys, which essentially draw air from far away from the asphalt surface where it is cold and then force the air over the sensor housing itself. And there's a heat sink attached to the back of these laser sensors that draw heat from the sensor, and then the cold air takes that heat away. So this way, the temperature inside the sensor is maintained at below the operating temperature of the sensor itself.
Share the screen for the online folks. Let me just jump in here.
Resume up for brief introduction. I got it.
Just drag it.
It's good. All right, so there were 2 demonstration projects.
Good?
Yeah.
Okay.
So there are 2 demonstration projects, one in Iowa and the other in Wisconsin. The project in Iowa was like a county road. It was a road in a really bad shape in terms of the surface. You can see on the top left that the road is, it's unraveled, it's patchy, and it was a county road. It had a very hilly terrain. There was a lot of changes in elevation, and it was also a road that had too many curves. So, and the project in Wisconsin was a regular highway, which meant that, it was a fairly flat terrain and there were not too many curves along the road. So we got to test 2 different types of project here. So here is the sensor in operation in Iowa, and on the left side is a thermal image of the entire system, just to see, how the temperatures are doing. You can see the asphalt is at like 250 degrees, whereas the sensor housing themselves are like close to 150 degrees. And this is the temperature in the housing, and I'm told that the temperature at the sensor itself, close to the heat sink, is much lower than this. Here is the same sensor in operation in Wisconsin. The asphalt temperature again is like 235 degrees, and the sensor housing reports a much lower temperature. So the data from the laser profiling system is basically collected into a data acquisition device and shown real time using a computer that you can mount onto your paper. So in real time, you could see the raw profiles, the localized roughness measurements, which is what is shown on the right side here, the power spectral densities, roughness histograms, defective reports, and fixed interval right quality reports. So this information you have in real time. So, and if you find that, you can see like a red line on the image on the right, and you can see that, that's your threshold for roughness. And if you exceed that, you might want to tweak the paver operation a little bit to bring it down. So post the paver operation, after the finishing roll is done and the asphalt is cooled down, we also profile the exact same location with a high-speed inertia profiler, just to compare the results of how it was behind the paver screen and how it turns out after the compaction is done. Right. So this was a proof of concept project. Like there are not multiple types of sensors that were tested or anything of that sort. It was just to see if we can even get a system that could do real-time smoothness for asphalt. And we must say that we did succeed in that fact. There's also any change you did to the paver operation, such as, you change the paver screed height, or you change the head of the material behind the paver, or if there were truck changes, all those kind of things were reflected in the measurement from the ORT sensor. This was more pronounced when an MTB was not used. This is due to the fact that when you use an MTB, the amount of material in your paver, the head of the material in front of the paver screed are more or less maintained a constant, whereas when you have truck exchanges and you do end dump into the paver, the level of the material in the hopper fluctuates a lot more, and then there's like stopping to accommodate the truck backing up to the paver, etc., which causes more pronounced effects. And we also found that post-compaction surface was relatively smoother compared to the pre-compaction surface. So overall, we did have good success in terms of using this setup. We were able to maintain the temperature of the sensor, inside the sensor below 120 degrees by cooling the system. And the installation process was also quite straightforward. Some of you might have noticed that the DMI between the two sensors was leaving like a small tire indent behind the paver screed, and but even that was just like behind the paver screed. Once compaction is done, we couldn't even see the line caused by that. One of the issues is that the sensor is mounted on the screed itself, and the screed is very dynamic in the paver operation. It keeps, moving, and this can affect your the profile data that we are obtaining. One such example is shown here. On the right is a schematic of the cross section of the screed and the paved material, etc. And any changes or any movement at the toe point causes this entire sensor assembly, because it's mounted on the screed, to tilt, and the tilting causes the multiple lasers to move in like different directions. So right now, the sensors to the left are moving downwards due to the tilt, and the sensor to the right is moving upward due to the tilt. And this causes a profile change that is not really a change in the thickness of the asphalt, but it's being measured by the sensor. So this is a shortcoming that needs to be addressed in future research. All right, so we also got some feedback from the contractors itself, and they generally said that the entire system was out of their way. It wasn't too much of a hassle to work around them, but they would prefer to have the entire setup moved, further back, so that they have some room to do, slope checks or depth checks, etc. And as I mentioned earlier, the DMI leaving a line behind the screed was an issue to them, but even though it was resolved when they went into compaction. Finally, the most positive feedback here is that they would consider this as a troubleshooting tool, that they are interested in seeing a real-time smoothness, and being able to tweak the paver operation is beneficial to them. So for the future, the recommendations here are to see if we could put the sensor not on the screed and on somewhere on the main frame of the paver itself. Therefore, we don't end up with issues with large screed movements affecting the results. And also, we would like to do more controlled experiments with the new setup, where you change the toe point to see if that affects your roughness. You induce events such as paver stops or truck exchanges, or expanding or retracting the screed, etc., to see if that affects the roughness measurements in real time. And finally, we would also want to make changes to the paver settings itself, to see if what how each change would affect the smoothness test. More details about this project and or more details on the recommendations themselves can be found in the report, which is online right now. We would like to thank NRRA for funding this study. We'd also special thanks to Todd at Caterpillar and Irv at Flyrel Consulting for their research partnership, and to Matt at Matthew Construction for coordinating the 2 field demos, and to the entire technical advisory panel at MnDOT and the broader industry. Thank you so much. I don't think so. They did use a Caterpillar paper, but I don't think the. Okay.
We used it here. We'll probably make the readings. Or there's some good vibes. Yeah. We have used what was called the ox claw screed. It looks like an upside down waffle iron. And it does get you more density. So the final surface probably will look more like what's going out of the back of that paver versus a regular one. So having this would probably be more valuable if you put those two things together.
Have you thought about doing GPS with this so we can integrate it into data?
That is a good question. I think the fact that this is a prototype, that they don't have, they haven't gone into that level of development at this point. But that is definitely a good idea to put in a, but you need like a more accurate, like RTK level accurate GPS.
So, and then on top of that, if you see this going through ProVal first, then it's beta, or going straight to beta. I know right now ProVal and beta kind of. But
I don't know if that's a political question that I should answer. I think.
Both softwares, so.
Okay, so I think I would say ProVal is the more suitable home for it. ProVal has profiles, and you could, like compare this profile with the post construction high-speed inertial profiles. So ProVal is the more natural home to this data than data.
has there anybody thought given to, similar to like a concrete curing cart, have it after the rolling operation? Because again, part of the thing you're trying to determine is the whole operation, while you're just kind of capturing the freshly laid stuff before it's rolled. Is there any thought of putting it on a cart similar to a curing cart?
So I think the idea here is to see the data in real time, not even like process it and put it into data or something, but it's to see the data in real time and tweak the operation on the fly so that we make sure that the material coming behind the screed is as smooth as possible when the pavers come in. So that is a good idea too, like to do it after the compaction is done as well. But I think their goal was more to like look at the.
Do you have any jobs planned this year?
Not that I'm aware of. Maybe George has a better answer to that question.
Any more questions? All right, thank you very much. So Curt, Dunn, and the flexible team is up next.
Okay, good morning, everyone. And so the flexible team's gonna would like to highlight one of their flexible team research projects this morning with a presentation from Dr. Joel and Sias. So before I introduce Dr. Sias, though, I just wanted to give a little update, I guess, is what we've been doing here in the last year for a few minutes here. So let's see. Oh, arrow, okay.
Yeah. Slider.
Okay. So right now we have about 24 research projects listed on the website, active in various degrees of progress. And before, just, a few months ago, we had them all individually on the project. And, based on what year they started, but we recently have regrouped them under 4 headings there, as you see there. I think I like that a lot better. I hope everybody else likes it too, but I think it worked out pretty good. So I think one of the biggest accomplishments we had in probably 2023 was the call for innovation. And I think I like the way it worked because we just identified some research needs that the states had, or the agencies. And then we asked the associate members to submit proposals based on those needs. And there were 17 proposals submitted for the flexible team that are related to the flexible team. And ultimately 5 were submitted or approved for funding. And so there's the 5 here. I won't go through them, but I think it really worked well. And I appreciate all the associate members that submitted proposals. Thank you very much for that. So another thing we got funded was phase 2A of the validation of loose mix aging, cracking resistance, evaluation, and balanced mix design. And so the principal investigator is Dr. Fanyan, if he's still here today, but from NDDOT. So we were glad to get that done too. And then wanted to throw just a meeting or like a team meeting slide in here. I think it's a really good place. I hope we're doing getting what we want on it. If there's something else we need to do, please let us know. I think it's a good place, a good forum for everybody to voice their ideas. It's informal. We always try to have a lot of good updates and then at least one presentation. And also, even just spur of the moment, we'll have a discussion on something, and we always have real good discussions, whether it's, text under seals or, any of those. And just wanted to say thank you to all the flexible members for all the, the good ideas that you've come up with and turning them into sound research. And then it gives us, the agencies, something to bring back to implement. That's really what it's all about. So I want to thank Jeff and Ben for their leadership and Lauren for coordinating all the NRRA stuff we do and making the website so navigable, real easy to get through. And also want to thank Michael for his, he greatly assists me in all my duties as the chair. So now I'm going to introduce Dr. Sias here. So Dr. Sias is the professor in the Department of Civil and Environmental Engineering at the University of New Hampshire. Her research focuses on characterization and modeling of asphalt materials and pavements, specifically with respect to recycling, cracking, and aging, and on the impacts of climate change on infrastructure. Dr. Sias is a past president of the Association of Asphalt Paving Technologists and is an editor-in-chief for road materials and pavement design. And her presentation is mixed rejuvenator test sections, phase 2. So please welcome Dr. Sias.
Great, thank you, Curt. Okay, so what I'm going to do is this is a project that we started almost 4 years ago. And so I'll go through a little bit of some of the summary data. There's a whole lot more data you can see on through some of the different task reports that are up on the website. And we've got a final report that will be coming out within the next month or two that will summarize all of the activities. So just as an overview of what we're going to go through today, I'll just give an overview of the project itself, go through just some select binder and mixture testing results, show you the pavement performance that we've got on these sections, and then a little bit about what's coming up in the next phase, which you saw as one of the projects that Curt showed. So just overall motivation and the objectives for this study. When this started, I guess the discussions on these test sections probably started closer to 6 years ago. There was really rejuvenators or recycling agents were fairly new and not a lot known about the long-term performance, whether with respect to the lab performance or the field performance. And there were some concerns with the effectiveness of these additives over time. And so the main objective of this project was to evaluate the effectiveness of 7 different RA products over time by comparing their performance to control mixtures. So this was all done with field produced materials. Test sections were constructed the end of August in 2019 up in Emily. So it was a 5-inch asphalt layer that there was 2 inches of mill and fill, and then 1.5-inch wearing course put down on top. And the wearing course had 40% wrap plus each of these different 7 materials, and then there were control sections that went along with it. So the RA section materials just in that wearing course. The section materials, again, as I said, there's 7 different RA products. These were added to 40% wrap mixes. And then dosage was determined by the suppliers. Okay, so the target was making sure that with that 40% wrap, you met a PG minus 34 target. Okay, so those dosages were done. And again, the target was on the extracted and recovered binder. So we've got the 7 test sections with the 7 different products, and then there were 3 control mixes. So there's a 30% control mix, which is the typical material that is used on the rest of the project out there. And then 2 40% wrap sections for the 2 different days of production that didn't have any rejuvenators in them. Okay, so 2 different controls, the typical that would be used, and then the 40% to directly compare with those. And you can see the dates of the paving on those. Now, one thing to note when I'm showing the results, as we were getting into the project, and getting some of the results, we were having the results for the second day, 40% control mixtures just weren't making sense. Something was not right with the material that we had. So all of that data is shown in the reports, but what I'm showing today, we've dropped that out of the direct comparison because there's something looked into some of the production, trying to get some of the plant information. Couldn't figure out what had happened with these materials, but obviously it wasn't a good comparator. So we're sticking with just the day 1 materials. So you'll notice that those aren't on there, but they are shown in the reports that are online. And one other thing to note, 6 of the products were added inline, and one of them was a terminal blended material. In terms of the overall project, tasks and the status, and again, all of these task reports are available up online. So we started with a literature review and interim annual updates for the first year and after the second and third year materials, and then a summary of plant produced mixture testing and the binder testing. And then the final report, we're in the process of finalizing that, and that should be out, and like I said, out for the TAP to review in the next couple weeks, actually, and then published probably sometime early summer. So in terms of the testing that was done, these materials had basically the kitchen sink thrown at them. We did almost anything we could that was available at the time, looking at these materials. So some of the testing was done by various NRRA agencies, and a lot of the testing for the further testing for the aged materials was done at UNH. So you can see a list of the different mixture tests that were completed, and then the binder tests. Most of the binder testing was done by MTE. And again, a lot of different binder tests that were done on these materials. Now, it wasn't just the plant produced material. We did a whole bunch of different aging conditions. So very comprehensive work in terms of the data that we've collected here. So for each of the test sections, we've got the plant produced loose mix, and that plant produced loose mix, we tested in the reheated condition, 6 hours at 135 degrees C, long-term aging, which was what was determined at the beginning of project as one long-term aging condition. And then based on some of the initial results, we wanted something that was a little bit further down the line in terms of the aging, and so added 7 days at 95 degrees C. So for all those mixture tests, we've got 3 different aging conditions. We've got field cores that we tested. So those were collected every year. And then for the binders, for all of those, binders were extracted and recovered from the original loose mix. Okay, those as extracted binders were also put through 20, 40, and 60 hours of PAV aging, as well as the extractions from the different loose mix aging conditions. For the field cores, we also have extracted the top ½ inch for each year. With an asterisk 3rd-year field cores, we had some issues with some contamination. So you'll see we don't have the results for those 3-year field cores, but we've got 1, 2, and 4. And then the inline sample binders were also tested, original RTFO and PAV aging conditions. So getting into some of the results, and again, not showing everything, but you will see everything in the final report. And if you're interested in some of the intermediate results, you can access them now online. Just looking at continuous PG for these, the way these bar graphs are set up, each set of bars is for each section, and they're just in numerical order from left to right. So the first 7 are the different RA products. And then you've got the last 2 are the 30% control and the 40% control. The field cores are the hashed bars. So those are the first 3. So years 1, 2, and 3. And then the next 3 bars, those are the extracted materials from the loose mix aging. So we've got the as produced material, the 6 hours, and then the 7 days. And I'm going to focus just more on the cracking since that's really where our concern is. So looking at the low temperature, you can see for all of the RA mixes, after 4 years of aging, they're still showing a lower PG, continuous PG, than the controls over 4 years. So that in-place material still showing performance that we expect over the 4 years. But once you get to that longer aging level, the 7 days at 95, they're getting close to that control material. So they're losing that effectiveness at that for the low temperature PG at the longer time. There is one that's a little bit more of an exception, that's 6006. You can see that's a little bit different than the others when you're just looking at the PG. But all the others relatively close. And if you're looking at the actual PG grade, they're all going to be pretty much graded the same way, or if they're off a grade, it's just barely off. In terms of the delta TC, okay, again here, graph is set up the same way. You'll notice that all of the field cores, okay, up through 4 years were below the crack warning limit. Okay, so still looking at, not expecting to see any issues with the block cracking. And they're all, very close to those control materials. Changes a little bit when we look at that longer term aging. Okay, so most of those materials are approaching or exceeding that crack limit, okay, at that longer term aging, and are starting to look a little bit worse than the control mixes. Okay, now you can look at this a different way. We've got the bars here, but what we've also done is just to show you how these materials are changing, okay, with respect to the controls over time with the different aging levels. So this is just the delta TC parameter. The top set of figures show what the differences are with respect to the 30% control. The bottom ones show the differences with respect to the 40% control. The first set of figures show you the field aging. So you can see, again, the trend that you saw with the bars, but you're seeing it quantified here, that initially a pretty wide range, but as we're seeing the field aging, these are coming closer together and getting closer to both the control values. The PAV aging, again, remember, this is the as produced material extracted and recovered, okay, and then 20, 40, and 60 hours of PAV aging. Again, you can see here with the additional aging, especially as you get to those longer term aging, you're seeing these all collapse together and come very close to the controls. And the same thing with the loose mix aging, the as extracted, and then the two different long-term aging, with the 6 hours being less severe than the 7 days at 95 degrees C. So it's just a different way of looking at the data. Now getting into some of the other tests, the FTIR, so looking just at the carbonyl ratio here in this particular figure, all of the RA mixes, regardless of the aging conditioner, have the higher carbonyl ratio than the controls, and that's with the different additives. Was not unexpected to see this, but you can see that it is happening. And again, as you expect, as we're seeing the aging, these are increasing a little bit. I will note that due to some of these different materials, we did have to adjust the way we were calculating the carbonyl ratio. And again, that's kind of detailed in some of the reports, but it does capture the full range of what we're seeing with those traces. And then again, showing how these are changing with the aging, same setup here. With the field aging, things are kind of staying relatively constant. With respect to the 30% control, with 40% control, you're seeing, again, those coming a little bit closer. With the PAV aging, obvious trends in terms of what's happening. And then same with the extracted and recovered from the loose mix aging. So that's just a quick snapshot of some of the binder results. Some of the mixture testing results. We'll start with some of the rheological properties. So looking at the Glover-Rowe mix parameter. So this is very similar to the Glover-Rowe binder parameter, where it's a combination of a modulus and a phase angle value at a certain temperature frequency combination. I will note with the mixture test, because we're testing some of the field cores, and the field cores have variable air void contents, to allow us to compare these, what we did do is did an adjustment of the rheological properties all to 7% air voids. So all of the lab testing was done at 7%, field cores variable, but we adjusted all of these to 7% to allow for a better comparison. So all of the rheological mix properties are adjusted. You can see here, again, these are set up the same way as the previous, except for here we do have the 3-year field core results. You can see that all the field cores have a lower Glover-Rowe mix parameter value, which again is better in terms of what we expect for cracking resistance. They're either better than or equal to the controls over 4 years. So it kind of supports what we saw with the binder testing, that so far in place, they're still maintaining that benefit of the RA over the 4 years in place. But we're seeing again with the 7 days at 95, the long-term aging condition, you see quite a jump, but there's still, most of these materials are still looking better than the controls from the mix perspective. And then same thing, looking at these specifically in terms of how the Glover Row mix property is changing as compared to the controls. Looking at the field aging, again, we're not seeing a whole lot of difference when you're looking at the control comparison over those 4 years. But then once we start looking at the lab aging, you're seeing those differences are the benefit from the RA decreasing, especially at that longer term aging. Now looking at intermediate intermediate temperature fracture, this was done with the IFIT tests. The IFIT, we don't have a way of converting for air voids. So anything with the field cores, those are in place air void contents. The lab mixes are 7%. So you can't do direct comparisons there, but you can at least compare to the controls. This does have an additional aging condition. Illinois DOT did these tests and they've got their own aging protocol of 3 days at 95 degrees C on a compacted specimen. So we've got that included in there. And basically takeaway from this is that once we hit the 3-year aging, we're below that threshold of 8. And now that threshold, that flexibility index threshold of 8 is based on, you know, an unaged material. But again, once we're aging, we're dropping down below that pretty quickly. You can see most of the reheated plant mix well above that. But then once you start aging these, especially getting to the 7 days aging, you know, you're at a point where none of these mixes practically are any different from each other. And again, you can see this specifically with respect to the control values, and you can see as, you know, as we're starting to get with field aging, you're seeing bigger differences, and then again, the lab aging as well. And then finally, the low temperature fracture test. So this is a DCT test. The parameter that I'm showing, this is not the fracture energy, but this is the post-peak index PPI index value. So it's a combination of fracture energy and parameters from the post-peak slope. So it's more similar to what you're used to seeing with the flexibility index. And again, with these, we're not testing field cores, but we have the reheated plant mix and the 2 long-term aging conditions. The test temperature with these corresponds to the test temperature at the site location plus 10 degrees C. And again, all of these are 7% air voids. So you can see most of the mixes, okay, are either better than or matching the controls once we get to that long-term aging. And, you know, we're seeing what we expect in terms of the decrease with aging over time. And again, you can see the plots here with respect to the 30% and the 40% controls with those different aging. Now, finally, getting into the performance of the test sections to date. So field performance. So the cracking field performance, I've got this plotted 2 different ways. The plot on the left shows you the total length of crack for each of the survey dates over time. And then on the right is a TC total, which is kind of a composite index that gives you an overall kind of view of where the cracking stands to date. So you can see from both the left plot and the right plot, the worst in terms of performance so far is that 40% control mix, the day 1, that's the top. And the best is the 30% control mix, which is the bottom one. And all the RA sections are falling right in between. And same thing when you convert that to that index value, all the RA sections are right in the middle. And there's really not, there's cracking out there, but not a whole lot of cracking out there to date. So that's part of the motivation for the next phase is we really aren't seeing any kind of differentiation in performance yet. So we need to give these a little more time. In terms of the rutting and ride quality, again, you can see everything's pretty close, grouped closely together. There's not much to speak of in terms of rutting. Ride quality is really good with all of these sections. These we only have up to 3 years. The next round of data collection, I think, is happening or has just happened. So we don't have that data included in these plots yet, but really not a whole lot happening on that side of things, which is good. So we're not seeing any issues with rutting with the RA sections out there either. Now, in addition to the field performance, we also did some modeling using the dynamic modulus and the direct tension cyclic fatigue testing results. And so looking at these performance predictions, we did it with two different material properties. So we did it with the as produced material, which is the yellow line, and then we did it with the 4-year field core data. And you can see, again, not a whole lot of difference that we're seeing in terms of the projected performance between these two sections. And all of them are falling between the 30% and the 40% control materials. So just summarizing what we found so far from the phase, this phase of the testing results. Okay, again, from the binder testing, our RA mixes generally showing similar or better PG low temperature and delta TC than our 40% controls through the 4 years of aging. When you look at the delta TC, they're a little bit worse, especially when you look at that longer term aging. And as I mentioned, they've got the higher carbonyl ratios for all the aging conditions. From the mixture testing, okay, again, most of those RA mixes still showing better performance, okay, for the 4-year field cores and for the 7-day aging. The intermediate cracking thresholds, once we get to those longer term aging, everything's basically hitting the bottom. Generally, those RA mixes have better values than the controls. But again, once you're below the threshold, nothing's really any good. And then the RA mixes initially are showing better low temperature properties, but then that's diminishing with the increased aging. For field performance, okay, all the mixes are showing better cracking performance than our 40% control, a little bit worse than the 30%, but again, not a whole lot happening out there. So really need to keep monitoring these over a few more years to see if we start seeing any differences in distinguishing the field performance. And then in terms of just looking at the aging protocols, this wasn't a main objective of the study, but kind of a side objective is because we have all this data, what represents what we're seeing in the field. That 7 days at 95 degrees C definitely is more severe than what we've seen so far with the 4-year field cores. The 6 hours at 135, based on, you know, the different binder properties, the different mixture properties that we're looking at, you know, that's really looking for these materials comparable to 3 to 4 years of aging in the field. And again, that's based on that top ½ inch of the field core. So it's the very surface. So it's more extreme aging. So in terms of what we're looking at going forward, continuing monitoring into the next phase of this project. So we've got a few more years of field performance monitoring, collecting the field cores, continuing to do the modulus fatigue. We're going to be collecting additional cores so we can do additional IFIT fracture tests on these, on the field cores, and then continuing to do some analysis with this. It's really a fabulous set of data that we've got with the binder and mixture testing to really look at lab and field correlations. And that's it. That's what I've got as a summary. So thanks for your attention and happy to answer any questions that folks have.
Any questions?
I'll take it.
Great, thank you, Joe. Very good presentation. I think up next now is Raul, I believe. Geotechnical. You, sir.
Good morning. Let's see if I calibrate the position. I realized like you have seasonal speakers like Kyle and Dr. Sias, and like yesterday, I feel like the microphone was very close, making some weird noise. I'm trying to calibrate and see it's better. You can see who's experienced and who's not. You know, I see these movies and rock stars like going like this with the microphone and you think that you're doing the same thing. And anyway, I apologize if yesterday I sounded weird. I will try my best to have it properly located. Before I start, I want to thank Lauren for all the help, technically speaking. We tried yesterday in our session all these weird things and everything was a success thanks to you and for sending you all these late presentation, all that stuff. So thank you, Lauren. I want to say that. Also, I want to thank Jeff Bronner, who is retiring tomorrow. Is our research manager. He's behind the scenes. He's behind the screens and all these efforts you see from all these research. NRRA is a key player. You don't see him here often in the podium, but he's a champion for all the work that we do on the different teams. So I just want to sincerely thank Jeff for all his advocacy. And I wish him a good retirement. Try to be as brief as possible. So we have currently 4 projects in the Geotech team, mostly all related to water management, to making sure you take the water out of your pavement system as quick as possible. And another project related to workload load restrictions when you have flooded pavements. Okay, those are the main areas. And the other project that we have active that is kind of relatively new is on measuring while drilling. And the idea behind this project, it was the attempt that we were trying to do as a team is to accommodate the fact that each DOT in the alliance has different structures. So let's say for MnDOT, the base and grading, the pavement foundation issue is located, like say in the geotech section. But other DOTs have that area located in the pavement design unit. Anyway, so each DOT has different structures. And technically speaking, geotechnical work involves more than just your pavement foundation, right? We have deep foundations, we have slope stability issues, everything that affects the right of way. There's a lot of work in the geotechnical space that involves the right of way. So that project, the team members really wanted to sponsor and funded the measuring while drilling project. So even though it's not really like road related, it still is in the realm of affects the right of way, and there is a lot of interest in that topic among DOTs. Geotechnical engineers in the DOT. So again, this is to accommodate the fact that the geotechnical sections and different DOTs are organized differently. So we try to bring a new project that try to have a bigger impact to all these other state departments. Okay, so the first top 2 projects here in this list were awarded in 2021, I believe. So they are more than 30% completed. We have made good progress. The first one we're going to be talking about after this slide. So Fyaz from Michigan State, we're going to go deep into detail. And I hope you enjoyed that presentation. We have worked a lot on presenting some of these preliminary results. And that will show you the importance of what we're doing right now. And I thank also Ben and the NRRA executive team in setting this up this way. Why? Because this allows for cross-collaboration, what did Professor Daniel say last night? Cross-pollination? Cross-pollination. And you'll see this project, you're going to clearly show like how impactful could be. We learned a lot from research from the ICT team. Kyle mentioned that project where they did the George Chan, Dr. Chan, and Dr. Sohail did the scanning, the mapping of Main Road using IC, construction in the foundation. You'll see how it's going to, that information, that project is informing the one in the top here in this table, and how hopefully that is going to inform the eventual perpetual pavement project. You will see there's going to be very important results that can be used to really understand the performance of really your products. Well, what happens usually is that we tend to overlook what the foundation is all about. You know, we do the spot testing, it passes the specs, so we go, okay, let's go and build it. But you know, we forgot that nature is not man-made, right? We don't have this concrete or asphalt that is man-made, and therefore there is always uncertainty on it. So you'll see by doing a simple mapping, proving of how it's uniform or non-uniform your foundation will give you a lot of information. So when you analyze if your product, if your rejuvenator, if your admixture in your PCC is not working, sometimes it's because you did have a non-uniform foundation. So this is going to help us move forward into evaluating technology that you have at the top. So second project, okay, the first project is gonna be an update after this. The flooded pavement, we're making good progress. There was some issues with scheduling because of trying to get students. So there's like about 6 months delay on that one. They're working on setting up the testing system in the lab for upscaling the app that they developed in phase 1. I think they're making okay progress. The third one, on the using of water repellency, I have few slides on that project, but I don't know, I was relying on Professor Daniels being here, so I'm good. I'm going to put him on spot. So I was working on getting these slides here, and I saw this chemistry. I was very bad at chemistry in high school and college, and I'm still bad. So I'm not going to pretend that I know exactly what this organosilane and all these connections mean. But anyway, the idea is to modify the water to make it hydrophobic and to have this coat in your base material that it will allow the water, it will have the water not to penetrate into your pavement system, right? So I don't know, Professor Daniels, you want to make a few comments on your project? These slides.
3 slides. I'll be surprised as which slides are there. So it's sort of like ad lib as we see. Well, look, and I want to be brief. I know we have Fyaz coming up, and plus there'll be an opportunity during the tour. So maybe I'll say enough to entice you to jump in the car and come to the MnRRA facility and help us troubleshoot, because we also have some field relevant activities going on in terms of premature pavement distress connected. But anyway, the general concept is, as Raul says, keeping water out of the system. And so there's lots of different ways of doing that. Our research vision generally is to be manufacturer agnostic and focus on the organosilane chemistry itself. So much like you have a whole potpourri of geosynthetic manufacturers out there, likewise, there's a lot of producers of organosilane. So we do have a particular product that we're using out there, but everything we do is intended to generalize how do you quantify hydrophobicity in terms of, there are measurements here. You see a little water droplet. You can quantify that droplet in terms of its angle to the horizontal. That's the contact angle. And relating that and other parameters to basic things like mineralogy, grain size distribution, density, so that we can actually design with this stuff and have performance-based specifications that any manufacturer can endeavor to do. So the section that you would see today, there's a very small test section, 150 feet, I think, for both sections total. Each section is 75 feet in length, just big enough to allow us to use full-scale equipment and to try this out. So the control, of course, is just designed as per the typical road for the clay soils that we have there. And then our treated section, there's different ways of rendering it hydrophobic. One way is taking the organosilane solution, which is typically aqueous, used but low viscosity, use as your moisture content, achieve your density criteria, and compact, let it dry. You don't have to wait any particular period of time. It ought to dry on its own. You can do that, or what we did here, which is a little bit more cost effective, but simply spray it. So this is analogous to like some kind of tack coat, although you're not actually sealing it, you're only treating the individual particles. And then you can see this is what that actually looked like. And so here's our treatment of the 3 layers. And then we have instrumentation in between. And I'm going to take my cue on how quickly you advance those slides as the exit stage left. But hope to see you this afternoon.
We did practice this, so this is awesome. Thank you. The other project that I'm very excited about is on the measuring well drilling, or MWD. So what I'm excited about this is it's a hot topic right now. Federal Highway is promoting this practice. And the idea behind, for those of you that are not familiar with this, is basically pretty much instrumenting your geotechnical rig. So it senses more. So you're more efficient during the drilling process. You may argue that, drillers have so much experience, and the drillers know, they feel it, and they can sense when you're doing a good job, when you're in a specific formation, if you're having trouble drilling, they know that. They don't know this sensing. But I'll argue that as a designer, this data coming out from this additional sensor is going to help us out, really assessing strength parameters, stiffness parameters, non-uniformity across that. So that's really, I think, what is the game changer with this technology, measuring well drilling. So yeah, we're going to have now several more parameters coming out live during the drilling process, and also the operator will be able to see with that nice device there what you're getting coming out of this loop system with your rig. So you're gonna have sensors measuring torque, how much fluid is coming in. So you know if you're getting lost, if you have any voids, you see if you've loss of fluid, you're gonna have a nice actual measurement of that as you go along. So that's very powerful, I believe. So you're gonna have profiles that look like that live, but you're gonna be able to also just get live all the strength parameters, you know, on shear strength, tip, friction angle, stiffness, all these geotechnical parameters, you're gonna be able to get it live as you go along. And one of the benefits that users so far have mentioned about this is that it will allow us to stratigraph, to be more accurate about stratigraphy of your subsurface conditions. If you have more questions, you can ask Joe Needfield there at the back. He's one of the members of the geotech section leading the implementation of measurement while drilling in our geotech section. So although in the table that I showed you earlier on, it only shows 5% progress, Nebraska DOT is leading this work. So the TL is Glenn Nicholas from Nebraska DOT and also Alex Silvey. They're doing an amazing job. We have met so many times. So even though it looks 10% of progress, we spend a lot of time trying to select the right system to make sure that all the alliance members are satisfied with it and is the best for the investment. So right now we have 2 systems available for doing that, the measuring while drilling, the GenLots and the LIM. And based on several evaluations that we have performed, the Nebraska DOT decided to go with LIM. And we hope that we can use that here and meet that, and that we hope that the other members of the alliance follow whatever we get out of this project in terms of guidelines of the use of this. And with that, sorry if I took too much time, Fyaz, for your presentation. I think it's fine. 998. I'll throw you.
Thank you, Raul. Good morning, everyone. Today I'm going to present about one of the new kind of geotextile called the Wicking geotextile and how it can improve the drainage and also the stiffness of the road foundation, especially in the wet freeze climates. And the PIs of the project is Dr. Cetin from MSU, Dr. Pupala from Texas A&M, and Dr. White from INGEO Geotechnics. And I want to especially mention Raul, the TL of the project. Actually, he's like a member of the research team. He's always, we are spending hours for analyzing the data. What is the, how the data is impactful? What is the meaning of this? So thank you, Raul, for all the insightful inputs in the project. And these are the tab members. We are always grateful for all their contribution in the project. So before I talk about that, how this geotextile can improve the foundation or improve the drainage, I want to talk about that how the frost action damages our pavements in the Midwest or in these wet freeze climates. So I think it is known to all in this room that during winter, we have the freezing temperature, and that freezing temperature goes down and it makes the water inside our soil converts to ice. And when that freezing temperature goes down, underneath everything is frozen. The temperature is hugely below freezing. But there exists a region called the frozen fringe region where water and ice coexist. So the pavement feels itself dry. So it sucks more water from the groundwater table. And if you have lower groundwater table, like in Main Road, 5 feet, 6 feet, then you have more water coming. So more water coming inside your pavement, and this water, because of the freezing temperature, converting into ice, and we are having more heaving into our pavements. So that's the scenario during the winter. The temperature gradient is going below freezing. Now, what happens during spring when the temperature is going up from the top? So the temperature is going up from the top, the ice is now converting back to water, but below it is still frozen. So those water which has those ice which have now converted into water, and since a lot of water came during the freezing event, so the pavement gets saturated because it doesn't have an escape path. Below it is still frozen. So that's when if truck goes, we'll have the damages in the pavement, and that's why we have the spring load restrictions. So because of this, we have these damages like potholes, cracks, rutting, and frost boil. And we need to also impose the spring load restriction, which is also a concern for the economy, the truck industry. So the background from this, we can understand that there are 3 conditions for this frost action. The first one is the freezing temperature. The second one is the frost susceptible soil. The third one is the water supply, or in more memorable terms, like Joel Ulding mentioned in his famous MnDOT video about these frost damages, 3 Ws: water, winter, and wicking. That means wicking means the soil which sucks more water. So how we can solve this problem? To solve this problem, since water is the main driving factor, if we can, like Dr. Daniels was mentioning, that if we can stop the groundwater from the groundwater table using water repellent chemical, that can be one concept. The other concept can be during the thawing, if we can take out the water with the help of some better drainage system or some kind of geotextile. So the concept here is we are using a new kind of geotextile called the wicking geotextile. So it has those black ions, as you can see, those provides the reinforcement, and the blue ions, those are the microfilaments, which has, as you can see, a smaller width and multi channels, which can suck the water with the help of the capillary action from the pavement. And after sucking the water, it can take out the water from the pavement. If you expose or the termination end of the geotextile outside of the pavement is in a drier environment compared to the inside, you have the suction difference from inside and outside. And because of that suction difference, water will come out outside of the pavement. So that's the working mechanism of this geotextile. So what this geotextile does, it does normal function just like other geotextile. It provides reinforcement, confinement, and filtration. But additional benefit it provides is that the moisture management and the drainage. So the objective of this project is to evaluate the short-term performance and the long-term performance. So for the short-term performance, we are conducting the large-scale accelerated laboratory test. And for the long-term performance, we constructed test sections at Main Road. We had 2 test sections. We constructed in last June 2022. And right now we are monitoring the performance of these test sections. And these are our tasks, and almost we're done with the task 6. Soon we'll submit our task 2, the task 7 report, that is the update of the second year, the monitoring results from the second year. So initially I'll cover that what we are doing, what we did in the laboratory testing. So for monitoring the performance in the laboratory, we constructed large test box. The length of the box was 6 feet. The width was 31 inch and the height was 38 inch. So we had 2 test sections similar. And in one test section, we had the control, no geotextile. In the other test section, we had the wicking geotextile. And we are simulating the similar environment we have and the similar material we have at Main Road, the sub-base materials, base materials, and the subgrade materials. And we have moisture sensors and thermocouples to monitor the temperature flow and the moisture, the way the wicking geotextile is taking out the moisture. So this is the test setup we use. As you can see in this picture, this is the wicking geotextile, and it has a open end in this side through which the wicking geotextile takes out the water. And we are compacting. And this is how we did the freeze-thaw simulation in our text box. So for doing the freeze-thaw simulation, we use the cold plates, and these cold plates are connected to the circulating bath. So the circulating bath has ethylene glycol, which will not freeze at -40°F also. So that circulating bath liquid, the ethylene glycol, is going on the top of those our box in those cold plates, and with the help of this, it's freezing the system. And this is the total setup. So we are simulating the exact environment, like we have lower groundwater table. So we have the water supply tank, which is going below our soil. So we are simulating the groundwater table with the help of that. And as I mentioned that we have the water collection container. The geotextiles are coming outside of the box, and we want to see visually that what is is it draining any amount of water or not. So those water collection container are for seeing that what is the amount of water coming there. And then we conducted the accelerated cyclic loading test. So this is our testing sequence. We did at first the freezing simulation. Then we did the thawing and drainage. Thawing and drainage is happening at the same time. Then we simulated the rainfall also. Then we provided time for drainage. And then we conducted the accelerated cyclic loading test. So the accelerated cyclic loading test we conducted at INGEO Geotechnics setup at Dr. White's lab. So this setup has some great advantage that we can do the random sampling of the load, just like the traffic in the pavement, that we have a small car going, then a large truck is coming. So the traffic distribution is random. It's not going from it's not going from low stress to higher stress. So it's very random. So we can do that, like 2.5 PSI of load is applied at the first, and then maybe 43.5 PSI applied. So this is the random distribution. Next, 20 PSI is applied. So this is the random distribution. And with the help of this random distribution, we can conduct a probabilistic analysis. So here we have the cyclic plates. With the help of a 12-inch plate, we are applying the loads, and we have the laser sensors, which is monitoring the deflections. And these are the test results from for the subgrade I'm just showing. So the system froze till the top of the subgrade. And as you can see, the interesting part is during thawing. So the red one here is of the control section, and the blue one here is the wicking section. So as expected, that the control section or both the section is supposed to moisture content should go up during the thawing. So what we are seeing that during the thawing, the moisture content is going up into the control section, as you can see here, but it's not going up into the wicking section. The moisture content is remaining stable there. And why it is happening? So we were collecting water in those water collection container. And what we observed that in those water collection container, visually, we could see that in the wicking section, there were around 11 pounds of water. And in the control section, no water was coming outside of the system. So that's why we're seeing that reduction in the moisture in between the water and the in between the wicking and the control section. And after this, all these simulations of drainage, and before conducting the cyclic loading test, we took, because the moisture sensor gives the moisture content at only one location, but we want to also know the spatial distribution of moisture. So for that, we take out moisture cans from 18 different locations in each test sections. We divided the test section into grids, and we took out moisture content at different locations to understand the spatial distribution of moisture. So as you can see, the top one here is control section. The bottom one here is the wicking section. So in the control section, you see more variation of the color. That means there is more variability in the moisture content. On the other hand, in the wicking section below, you see less variability in the moisture. So that shows the benefit that wicking section is maintaining the uniformity in the moisture content. And these are the test results from the cyclic loading test. So as I mentioned, that since we are able to apply 100,000 loading cycle, and also we are doing the random sampling of the load, so we are able to conduct the probabilistic analysis. So what this means is that in the x-axis, I have the permanent deformation. In the y-axis, I have the probability of having that deformation. So as you can see here, suppose if we set our design criteria that we want deformation less than 0.25 inch in our pavement. So what is the probability of having that in case of the wicking section? So as you can see, in case of wicking section is 52%, having deformation less than 0.25 inch. Suppose that's a hypothetical design criteria. We can set our criteria based on the design. On the other hand, for the control section, the probability of having is 22%. So we want lower deformation. So the wicking section has 30% of higher probability of meeting the design criteria. Next, I will move on to the field test section. So we had two test sections constructed, as I mentioned, in the June 2022 construction season. We had two test sections, one control and another wicking section. Both the test sections were of length 250 feet, and this test sections were also part of the intelligent compaction project and perpetual pavement project. Already Raul talked about that. What is the importance? I will show some results and I will discuss more on those, the importance of the understanding or the importance of the collaboration between the teams. So this is the layout of the cross section of our pavement section. So we had, since this was part of the perpetual pavement project, the pavement structure layer was really thick. It was around 29 inch, and we had sensors, the moisture sensors and magnetic potential sensor, which can show us what is the drainage capability of the wicking geotextile along the cross section, along the width of the pavement, and also along the depth of the pavement. And also we had a new kind of sensor, the shape array sensors, which can give us the deformation into our pavements. So this is how the wicking geotextile was laid out at the interface of the subgrade and the subbase. And so initially I mentioned that how the wicking geotextile works, that the conventional design or the manufacturer recommendation design is that you need to daylight the geotextile with a slope in the sides. But that's not always feasible when you have a flat pavements like we have in the main road, it's not possible to daylight the geotextile here, and you need to excavate all this amount of soil. So the design procedure we followed here is that we need a drier environment. The termination end of the geotextile should be in a drier environment. So for creating that, we excavated trench in the shoulder with which has width of 3 feet and depth of 1.5 feet, and we fill that trench with the gap-graded aggregates. So the idea is the gap-graded aggregates will dry fast, and which will give that drier environment compared to the inside of the pavement, and the wicking geotextile can drain the water because of that suction difference. And above that gap-graded layer, we put the non-woven geotextile so that there is no intrusion of fines, and we can get that layer dry fast. And this is the sensor installation, and we install the shape array sensor. So how this sensor works is that you can consider two pens, two rigid segments, and in between the pens, it can move up and down in the joints. So as you can see, the first one, there is no movement, and at the joints, if you have heaving, it can go up. If you have settlement, it can go down. So from that, you can compute the deformation into your pavements with the help of the sensors. And here we are installing the thermocouple tree. As you can see, Jacob from MnDOT and Glenn, the former director, he's also making his hand dirty in installing these sensors. So that's the beauty of the NRRA, kind of everybody's working here. So this is the sensor installation. As I was talking, that we have 5 sensors along the width of the pavement, the moisture sensor and magnetic potential sensors. And these are the field tests during construction. As I mentioned, that it was part of the intelligent compaction project. So the test sections were divided into finite grids, each of 25 feet length and 6 feet width. So we conducted, the whole team conducted the nuclear density gauge, the MnDOT team we conducted the DCP test, the UTEP team led by Dr. Sohail Nazarian and Dr. George conducted the IC mapping and LWD test on these test sections. So from these results, both the test sections perform kind of showed the it performed the criteria for stiffness. But was these two sections similar in terms of comparison? Because that's very important if we want to compare one section to the other, that what is the stiffness of this section compared to the other section, we will see in our results. So this is the moisture content profile of the sub-base layer. So here we are plotting the relative change in moisture content compared to the initial. So if you see here that the moisture content in both the section is going down during that freezing period. In the below graph, I have the temperature in the y-axis, and in the x-axis, I have the time. So from the construction period, that is when we started collecting that data from October, and now we are in February, April or February. So we have all these data, and during the freezing, the moisture content is going down because water is converting into ice. And at that time, the moisture content is going down. But what we see during the thawing is that the peak in the red line in the control, the moisture content is going up. So, but in the case of the wicking, the moisture content is not going up. So it's always continuously keeping below zero. So the change is always, it's not increasing. The moisture content is not increasing in the wicking section. On the other hand, in the control section, during the thawing action, the moisture content is increasing. And also during the rainfall events, so if you see these are the rainfall events, during the rainfall events, we are seeing these peaks into the control section. But in the wicking, it's always maintaining uniform moisture content. So from these results, we can see the data in another terms, in terms of probabilistic analysis. So in the y-axis, I have the cumulative density function. So from all these data of last 2 years, we plotted this graph. And from this graph, what we can see is that, so what we want, that we want that the moisture content should not increase from its initial construction, or it should dry up. It should not increase. So we want below zero. The change should be below zero. And here we are seeing that in the wicking section, there is more probability of having that. On the other hand, it's the less probability of having that in the control section, the change. And this is the probability distribution graph of the relative change. So as you can see, at the bottom, the peaks, these peaks, the narrow line. So that means the moisture content is always remaining uniform compared to the control section in the wicking section. And also, so that's the bottom peak is because of the optimum, because pavement always wants to come at optimum level. And at the left, you see those peaks are because of the freezing, because during freezing we have lower moisture content. I will discuss more in that next slide. The other peak here you see during the rainfall, so the moisture content is increasing. But if you see closely that peak is only in the control section, we are not seeing in the wicking section. So that shows the benefit that during the rainfall events, we are not seeing the higher moisture content trends in the wicking section. So some more insights on the distribution curve. So as I mentioned, the bottom, the middle one here is of the optimum moisture level. But what is the one in the left during the freezing? So what happens during the freezing? As you can see in my x-axis, I have the time during the month of December, January, February, the moisture content is going down because water is converting into ice. And when moisture content is going down, the matrix suction is increasing. And basically, this is the driving factor for freeze thaw damage, that when the moisture content is going down, the suction is increasing, which is pulling the water from the groundwater table, and we have more water, more damages in our pavement. So from this data, we can plot the soil freezing and soil thawing characteristics curve, like the soil water characteristics curve, like Dr. Bill Lycos was mentioning yesterday. So as you can see in this graph, when the moisture content is going down, your suction is increasing. And then we have a nice hysteresis during the thawing. We see that hysteresis, and during the thawing, again, the moisture content is increasing and your suction is reducing, but there is a hysteresis. So at the same suction level, suppose if we consider 40 kp of suction, at the same suction level during the thawing action, we have higher moisture. So why this is important? This is important for the finite element modeling. For accurate modeling of your pavement section, for validating this model, you need these basic parameters, like the unfrozen water content, the soil freezing characteristics curve. If you have these parameters, you can accurately predict with the help of the finite modeling that what is happening in the pavements. So that's why these are very important, and we are currently working with the modeling of this. So with the help of the finite element modeling, we can reduce the number of test sections if we can validate the model with the real-time data in the pavements. And this is the moisture content distribution of the subgrade. So we see the similar trend here, that more uniformity, the blue line, blue zone there, more uniformity, zone is narrower there. On the other hand, in control section, as you can see, higher moisture content. In the x-axis, I have the moisture, so higher moisture content in the control section. And also more variation in terms of moisture in the control section. And this is the spatial distribution of the moisture. So we had 11 sensors there. We have sensors in the subgrade, we have sensors in the subbase, and this is showing the variation for one of the time step during the spring. So as you can see, in the left, I have the control, in the right, I have the wicking section. And as you see in the control section, there is more variation in the color. So more variation in the color means more variability in terms of moisture. And on the right, I see more uniformity in the color. So the moisture content is more uniform into the control section. And these are the shape array results, the shape array sensor, which was measuring the deflection in the pavement. So during the springtime, so I am plotting for the two segments which are inside the pavement, the deformations. And as you can see, the red and black line, those are of the control section. We are seeing more settlement during the thawing. On the other hand, for the control section, we are seeing less deformation here in the blue line and the green line, less deformation in case of the control section. Also, that with the time after the spring thaw period is over, when we are moving into the July, August, we are seeing that those blue and the green line is coming back to its initial condition. It's regaining its initial condition. It wants to come back to its initial condition because moisture is getting drained. But on the other hand, control is having that residual deformation. The permanent deformation that it had, it's having there. So based on then after that, we conducted also the FWD test. Thanks to Jacob for conducting this test and sending us the data. So for the FWD test, as you know, we have 3 drops, and we are plotting this deflection basin with the second drop, so 40 kilonewton load, 9 kips. And what we are seeing here is that in the control section, we are having less deflection in terms of the FWD results. So that's interesting because the wicking section was draining out the moisture. It was showing us less settlement. But in terms of FWD, when we are seeing the results, we are seeing a variation in the D0 of 10.2%. The control section is having less deflection from the FWD results. We wanted to analyze more these results, and I love the approach from Dr. Iab and Thomas study they showed yesterday for analyzing these data instead of the conventional procedure of going with the modular. So we computed this base damage index, which is an indicator of the structural condition of the base and subbase. And also we computed the base curvature index, which is the structural condition of the subgrade from these deflection values coming from the FWD. And we are seeing a similar trend that control section is having less deflection, 14.5% variation. So we wanted to understand the results. So we went back to our initial conditions, the intelligent compaction results. Thanks to Dr. George and Dr. Sohail Nazarian team for conducting this test and providing us with this value. So we see that the compaction, we see the compaction meter value in the y-axis and the different materials here. So compaction meter value from the intelligent compaction is indicator of the stiffness. And we are seeing a lot of variation in case of the coefficient of variance, the variation in between the test sections. So my green one here is the control section, and the orange one here is the wicking section. So we see the variation of around 11% between these two test sections, coefficient of variance of 19% and 31% in the wicking section. So that's actually contributing to the subbase. Also, there was a rainfall event during the construction of the wicking. So these all factors, as you can see the intelligent compaction mapping there is in the control section, there is more uniformity in the color. These are the CMB values. And on the case of the wicking section, two different colors, yellow and red. So complete two different lengths, different values in the stiffness. So that's actually contributing. And if we see the mean value of all these stiffness parameters, so if you see in the subbase, there is a variation of 46% in between the control and the wicking. Control was way higher, stiffer compared to the wicking section during the construction, during the initial conditions. So that's actually impacting in the FWD results. So in the FWD results, we see that the variation is 10 to 15%. So because of the wicking geotextile is draining out those water, from that 46% variation, it's bringing out, it's lowering down that variation. So it's now 10 to 15%. So if we had just compared the data without considering all those initial conditions, we may say that no, this test section is not working. But when we bring this parameter, so from 46% of variation, it's bringing down because of those drainage. So it's very important to have those initial conditions mapped, and we can understand what is the variation in the initial condition. Because when we are comparing between test sections, one thing is meeting the design criteria, and the other thing is when we compare both the test section should be orange to orange. It should not be apple to orange. So we want to compare orange to orange. But the problem is that we have nature there and we cannot control all these. So the mapping is helping us understanding the results from that perspective. And also those mapping results is also matching with the LWD results, the spot test results. So we are seeing the same variability, like the coefficient of variance, as you can see. Huge variation in the wicking section. We have 25%, in the control we have 12%, and also similar variation in the stiffness, 45% of variation. So the conclusion from our study that, as we see from the moisture sensors and also the spatial variation in the moisture, that wicking geotextile is draining out the water. And the settlement during spring thaw, we observed from the shape area sensors that the control section is having more settlement. But when we conducted the stiffness test with the FWD, we are observing that control section is having more stiffness or less settlement compared to the wicking section. So there is a variation of 10 to 15%. But the initial condition, so there in the initial condition, there was variation of 46%, which is impacting that 10 to 15% variation. With time, wicking geotextile is bringing down that variation. So finally, the most important thing that thank you NRRA for funding this research and all the help in this research. Thank you, Raul, again for all the help in the analysis. A special thanks to the MnDOT team for helping during construction, installation, and field test. The MnDOT team was really great for helping us. I remember a lot of instances like there was one Saturday we had to work for doing some sensor. Emil was there for helping us with those. Then one of our shape area sensor just broke, and we were kind of the sensors are expensive and what to do. And there was one super guy called Bob. I don't know. I think he retired right now. So he helped us. He came back with all those kind of our whole research team was down that what we will do, because these are, if we don't have the sensor, there is no way to get back the sensor. But he came, he patched the sensor, so we get the sensor live. Then our one of the thermocouple tree also broke. Michael was there teaching me how to make the thermocouple tree. So we again make the thermocouple tree and install it. So thank you all the MnDOT team for all the help. Thanks to Dr. Chetin's research team. Sinan is here. So he was a former colleague at MSU. He is now with Wisconsin DOT. Zeren is here. She was doing the internship. So thanks to all these people, thanks to Dr. White's team for all the support in the field, laboratory tests, and also grateful to the TAP members for their feedback on the project. So that's all from my side. Thank you. I will be happy to have your questions.
So, first of all, it's based, so from my understanding, the ice lenses are based on the, the hydraulic conductivity and also the particle size. Did you get any tests of, what I'm seeing an in-road salt plane, right? It's a plane of those, if you could test those things. If not, it'd be interesting to see how that kind of compares to the Wicking, 11 pounds of water industry kind of correlate that. So, and just the other question was any indication of how long it sounds like it'd be a really good performance, but how long it lasts, how long you're going to keep going to make sure it keeps wicking.
Of course, I will answer the second question. So I think Dr. Technical, I think we just got extension for monitoring for the next year. I don't know. We are going to monitor for the next year also, but I think the geotextiles will be there, and we can keep monitoring. The sensor will be there. So as long as the sensors are high, we can keep monitoring. We will always get without. And in terms of the ice lenses for the wicking and control, we didn't compare that. But for other different projects, we are comparing the different ice lenses. We are working with Dr. Daniel's team and to see these ice lenses and everything. And for the other project, but for the wicking, we didn't do it. Thank you.
I'm Terry Beaudry, a green base engineer. This has already been somewhat implemented, so we do have a specification. The 3733 is a type 13 geotextile from Minnesota people. We did use it in a project last year, District 8, in reclamation, where we did an initial reclamation and we picked that up 10 inches and we placed it below. So a long project, so we'll see how that works out. And and then one of the reasons I wanted, I think this was maybe mine, Raul's research project initial idea. And one of the things that we really want to come get to is where the credit should be within the MnDOT program, right? So what is it, if you're in the GE, and there's some waffles here, how many inches of gravel would be working that in the MPUG is, kind of resulting modulus benefit are you getting from the project? So looking forward to that result and getting it. Thanks.
Thank you. Thank you, Ben.
No, we're getting a great set. I get excited about this. Okay, so I hope you guys get the message. One of the messages was cross collaboration between teams. What is very important here is the mapping the technical fashion, especially in our facility like MnDOT, where we are spending a lot of money with the products, with instrumentation. It's good to know that we are normalizing that it's a fair field for all these products that we are applying, right? This clearly shows that we didn't have that mapping. We have maybe draw the conclusion that all the Wicking geotextile is not working well. As a matter of fact, it was like, oh, starting from the get-go, it was an unfair condition because the software is significantly less uniform and less stable. There are two other cases that I'm going to bring up later on. People get excited. I didn't have time to finish the estimation, but like for example, for the other project on recycling, using recycling techniques for perpetual pavement, cells 1, 2, 3, 4, like the mules, the TL. There is no unexpected results from some of the analysis that have done on fracture energy on the asphalt binder. So they're trying to see, if we add this rejuvenator, if my fracture performance improves. And there is cell 2, the results are showing way higher results compared to the other ones. And one of the indications, unfortunately, we didn't delay compaction there. Thank you for Glenn. Glenn really we put Bernard and I came and asked him, can you help us out with this fund? We're gonna need to scan this. Thanks to Glenn, a little bit of getting to prove that it's important, especially in our research facility, doing the technical compaction on your foundation. The foundation matters. So some of these results are we have like these 3 or 4 case studies where showing the importance of accounting for your uniformity of the foundation. And so stay tuned, we'll get more results. And I hope that was the message that taking into account the foundation is very important to look at this thing holistically. And I hope that this information that you got here is going to inform the next team that was going to get the award. I don't know, it's going to be still, it's kind of awarded the perpetual payment project or not? Hasn't been like. Okay, so it hasn't been that. So hopefully the people that are going to be applying for it can review this information. It's going to be very useful for the flexible team in their awarding on this for the perpetual payment section. Thank you.
Great. We will take a break and reconvene at 10 a.m.
Okay, my name is Tom Burnham. I'm the chair of the Rigid team of NRRA. And today I'm going to give you an update on some recently completed projects, some active ones, and then we're going to have a presentation on another active project. So I'm going to just kind of start by describing some of the recently completed projects. The first one is the effect of low and moderate recycled concrete aggregate replacement levels. And this is a project about, there's been some studies where we're using, very high levels of recycled concrete aggregate back into the concrete. Well, this was, well, what if you're at the low end, like 10 to 15%? What effect does that have? So again, I'm just going to kind of describe what the project's about, and later I'll show you the link. Or you can always go on our project webpage to get the results. The second project that recently was completed was the one that has a very long title, but essentially it determined the kind of mixes that we put into the new concrete test sections we built in 2022 at Min Road. So again, because of the nature of the mixes, many of them were what you say exotic, something we've never worked with before. We hired some national experts to come in and kind of help us determine what those materials were. And it was not just picking materials, but what kind of testing should we do? Because some of these may not be suitable for some of the standard testing that we normally use. Another project that just wrapped up maybe last week was the one about mitigating dowel and tie bar cracking. That was about, there's been some observations of projects around the country where we get this unusual cracking, and this project was about trying to look into, is it due to the dowel bars or the tie bars or something? So again, I'm not going to go into the results. I just wanted to kind of point out that these are projects that have been going and are now recently completed. Now getting into some of the active projects, we have another project. Actually, this is getting very near completion, and that's about the development of a pavement-specific structural synthetic fiber. For a long time now, we've been using fibers in our thin concrete overlays to enhance, kind of keeping them from shifting around or transferring load across joints since we don't have dowel bars. And this is kind of phase one of this project about understanding what are the forces that we have to, that a fiber would have to do to help, transfer load across these joints. Because right now, pretty much what the industry uses is the fibers that come out of the flooring industry. And of course, what we're discovering is our loadings are far different than anything that's going to see in an industrial building. So far, the fibers have been helping kind of keep the panels from shifting around maybe on the longitudinal joints, but as far as transferring load, they're not suiting to what we're looking for. The next project's alternative cementitious materials. This is part of 3 projects, again, that are involved with those 2022 concrete sections that we built. And we're going to be hearing an update from Prashant here shortly after I get done here. Another one is alternative pozzolanic materials. And then the other one was the use of carbon dioxide, so carbon injection. So those are 3 projects ongoing, multi-year projects, and they're really designed about going out and monitoring what's happening in those new sections and understanding, whether these materials work and will they be a benefit of the goal of really helping in our sustainability efforts. The next project is using early loading to increase joint deployment in concrete overlays. So this is what we're finding is that in the thin concrete overlays, we'll go and saw these little joints, and then we go out and discover, well, maybe half of them deploy. And so ideally for, when we design, we expect those joints to all deploy. So there's been some experimentation in some of the districts with, let's put a truck across and try to snap these joints early in their life so that they activate sooner. And so we're kind of looking at that, looking into whether that is a successful practice. Another project that I'm the PI on is repairing these thin concrete overlays and then diamond grinding, because we're finding at least in Minnesota, we tend to get faulting when we get heavier traffic loads. So what happens if you repair some of the busted panels and you do a diamond grind? How long does that last? So we're trying to evaluate that. The next project is the automated 3D GPR analysis that was mentioned this morning. That's going to be a brand new project just starting up. Another one that we're going to be building as part of new test sections this summer, we're going to be building 8 more of them on the main line. And one of those is the use of polymeric microspheres to replace iron training. So very interesting concept that it's been tested maybe a decade ago, but apparently the technology is advanced enough that we're going to give it another try. And then another one that we're going to be going to RFP very soon is, again, support of all these new sections that we're building this year. So it's going to be very similar to those other 3 that are ongoing. So again, anytime you're interested, we have our project webpage you can go to, look at all the past projects that have finished, see all the task reports, and also, see where we're at with all these projects. Now, something that I missed yesterday was announcement of the international conference. We're blessed here, or maybe I'm cursed, I'm the chair of this, but we're having the 13th International Conference on Concrete Pavement here in Minneapolis in August. Hopefully most of you have all heard about it. If not, I got some flyers I put some on the table. I see they're gone. But part of that is actually NRRA is going to have a 4-hour workshop. So we're going to be putting, more findings and stuff than we could cover today during that conference. And again, that's, I think it's going to be a really successful conference. We have over 20 countries, very international, so you get a very broad experience. We continue to look for sponsors, exhibitors, plenty of opportunity. There'll also be a Min-Road tour at the end. So again, I encourage you, if you have interest, please sign up and be part of this. With that, I'm going to turn it over to Prashant Ran, who's a senior engineer with Applied Pavement Technology, and he's one of the PIs on one of the teams that are monitoring the performance of these test sections from 2022. Please welcome Prashant.
Thank you, Tom. So as Tom mentioned, this is one of the 3 parallel ongoing projects at MnDOT. And this one particularly is focused on alternative cementitious materials. So if you are not familiar with what an alternative cementitious material is, essentially what we are looking at is anything that can be used to replace Portland cement clinker, right? And that is, and why are we trying to do that? And the main reason is because of sustainability concerns, right? We want a greener material, and some of you might have even seen the PCA's road to carbon neutrality for concrete. I think one of the strategies is using alternative cementitious materials. And ACI also published a report on alternative cements. If you're interested, looking at what do we need to do in terms of mix designs, what are some of the testing methods that are applicable, and that's a great report, and that's out there. And we did summarize parts of that as a part of the lit review for this particular project. All right, looking at, and before we get started, I just wanted to mention the project team here. Applied Pavement Technology, we are the prime contractor on this, and we have NCE, WJE, and Larry started working with us on this project. And I would also like to acknowledge the TAP members. Our fearless leader, Tom, is right here, and several other members who have been very, very helpful in reviewing the documentation, providing great valuable feedback as a part of this project. And I didn't put the names here, but I also want to acknowledge Jacob and Rob as they provided a lot of information during the construction of the test cells, and they were really great. Thank you. All right, in terms of objectives, so what did we want to do with this particular study, right? The first aspect was really determining, okay, what do we need to consider when selecting some of these alternative cementitious materials, particularly for pavement applications, right? One thing that we did not want to do is we did not want the batch plants to change the way they operate. We did not want any special handling, mixing, any special requirements for these particular materials. That was number one. And number two was we did not want to change the way pavement construction operations are performed. The typical slip from process, no modifications, and can these materials be used for that? So that was one of the things. And then what testing do we need to do for acceptance during the paving and for acceptance requirements? Really, there are no special test methods that have been devised so far that are specifically designed for alternative cements. What we've been doing is use the existing test methods and maybe make some minor changes along the way. But really, there is no special test method that has been designed just for alternative cements. And like I mentioned earlier, one of the main focus of this particular project is we want to reduce the environmental impact. Right? Can we reduce the global warming impact coming from some of these paving materials? And at the same time, we do not want to lose any the durability and performance. Right? Those are main aspects. So that's why we want to look at the field performance. The main objective is going from lab to slab, right? And then from slab to actual maybe demo projects or maybe a larger scale project. So that's the intent of this particular project. All right, we have several different tasks here. We've gone through tasks 1 through 4. This is a work in progress. We completed, the construction was completed in 2023, 2022, and we had the year 1 performance inspection in 2023, fall of 2023, and then we will be doing the second round of inspections. The year 2 inspection will be performed this fall. And then the first 4 tasks are completed, and task 5 is, will begin this fall. All right, looking at the materials, we have 5 different test cells that we're monitoring as a part of this project. The first one is ultra high materials, and this one, the manufacturer said this supposedly has 0% Portland cement clinker. AET did do an XRD testing to confirm that it does not have any Portland cement clinker, and we don't really know what the material is. We thought it could be a CSA type cement, but we are not sure. The initial formulation that Ultra wanted to use was an alkali activated cement, but they could not dial down the mix design. So then they provided another formulation which did not have any Portland cement in it. And material number 2 there, Astro blended cement, that's a type 1P30 cement. It's a blended cement. And then the third material there is a Tennessee to Opus SEM. This is a manufactured fly ash, or as they call it, a manufactured alternative supplementary cementitious material. The mix was a type 1P10 with 35% replacement for cement for this particular manufactured fly ash. And then test cell 4 was a study control, a typical MnDOT paving mixture. And the last test cell there, 22-23, was the continental blended cement. That was a type 1L20 with 30% fly ash replacement. And more details on these test cells, the thickness, I think these were all 7-inch cells. And if you open up your NRRA 4 folder, the MnDOT has a nice little pamphlet there providing you with the details on the test cells. And looking at construction testing, right? This morning, Joe mentioned that they threw the kitchen sink as part of their testing. Well, they threw 2 kitchen sinks here, and maybe even a few smaller bathroom sinks. So we had the AET do a bunch of testing, and then we also had the FSWA Mobile Concrete Technology Center come in and do some shadow testing. And then we also have additional testing that is currently being performed. We're still waiting for the results at NIST in DC, and also Turner Fairbank is also involved as part of this process. So a lot of testing, anything you could possibly imagine, it's probably in there. And then I'm not going to show you the test results from everything. I'm not going to bore you with everything. I'm going to focus on the field, the results, and a little bit of the lab results. All right, fresh concrete properties. Again, I'm not going to go through all the cells in this table here. And then we the air content, the typical one, and then we also did the super air meter. And then, as you can see, most of the properties are pretty similar to what you would expect from your conventional paving mixture that is shown on the very right, the study control. And then with ultra high, you see some glaring issues there. The air content 9.2%. So the issue was, as I will show you in a little bit, initially they did have some problem dialing down the mix. They did add the viscosity modifying admixture. They didn't have the right quantity of the water reducer, and there might have been some contamination at the batch plant, which resulted in a very, very stiff mix initially, but they did improve the mixture as we went on. But a lot of the air that you see there is probably entrapped air. And I don't even know if they could do the testing properly with some of those initial mixtures, because the material that they got to cast do the fresh concrete testing and maybe even cast some of the concrete cylinders and the beams were less than ideal for that particular material. But overall, properties were very similar to what you would expect from your typical conventional paving mixture. And this was the testing performed by the Mobile Concrete Center. And then looking at the modulus values, very, very similar in the 4 to 6 million PSI range. And the Poisson's ratio was also, in the 0.2 range, which was very, very typical of what you would expect from your paving mixture. And then quickly looking at the compressive strength results, as you can see, some of these materials have a slightly lower rate of strength gain, particularly the one at the bottom that you see. I believe that's the Terra CO2, which had, I think, 35% replacement, but slightly lower rate of strength gain, but overall, nothing out of the ordinary. And then when you look at the flex strength, one glaring observation you see is the ultra high, which has going up and down. That's mainly because they could not really cast proper specimens there. So I would take the results for ultra high with a grain of salt, because the mixture that was received was very stiff, they could not make proper specimens. And quickly looking at the RCP test, people still do the RCP test. It might become extinct in a few years. Maybe the bulk resistivity testing might replace this. But anyway, this test was performed, and as you can see, for ultra high, very, very low permeability, corresponding with high resistivity, as I will show you on the next slide. And overall, all these mixtures are within the low to very low permeability range. And then quickly looking at the bulk resistivity testing, as you would expect with the ultra high, which had very low permeability, you would expect high resistivity. And then in general, it is probably a magnitude of scale, away from the other materials. But overall, I would say all these materials had, would exhibit very, very low permeability. And that should correspond to long-term durability aspects. So in general, from the laboratory testing that was performed, we saw that the fresh concrete properties were really compatible with conventional mixers, right? And then the compressive strength values, they did do 56-day values also, and then they exceeded 4,000 PSI for all the materials except Terra CO2, which was close to 4,000, but slightly less than that. And as you saw for ultra high, there was a lot of variability, and then probably due to the some potential contamination at the batch plant, and also the failure to add the viscosity modifiers, and then also the water reducers in some of the initial mixtures resulted in a lot of variability. And then no issues with the 56-day compressive strength values for most of the materials. They exceeded 500 PSI, well within the requirement that MnDOT has. And as you saw on the previous slides, the RCP testing and the resistivity testing did show that these materials have very, very low permeability after 56 days. And quickly looking at the constructability evaluation, we did look at a lot of aspects to evaluate, okay, are these materials really suitable for a typical paving construction? A lot of this information has been published in the report that should be available on the NRRA webpage. We looked at material handling aspects, workability, equipment used to place the materials, ease of finishing and texturing, and also whether any adjustments needed in the field for some of these materials. We did have to add some extra water for some of these mixtures to achieve the required workability. But all that information is documented in the report that on the NRRA webpage. So a lot of these materials were delivered in super sacks. These are huge bags, 2,000-pound bags that are not really convenient for moving. And especially if you have some blended material, 2 or 3 powders that have been blended together. We saw that for some of the materials, it was not really a homogeneous mixture, so that might also have resulted in some mixing issues. But these super sacks were transferred into a pneumatic tanker that was used in the central batch plan, and that is not ideal. It was quite a process as it was mentioned to us. And for the first 2 loads, like I mentioned, were excessively dry. I will show you a couple of video clips if they play, but then the batch plant realized that they forgot to add the viscosity modifying admixture and the water reducer. And then we had to wait 45 minutes for the next batch, which came out. That was slightly better. And then I think the third batch was much better. But then one thing we did observe with this particular material was it loses workability very, very quickly. So I think one reason is we did not have enough time to dial down the mix. This is not to say that, okay, this is not a good material, but we need to do a lot of trial testing and batching before we really apply it on the field. And there might be another opportunity this year. I don't know if new test cells open up, but that's something I wanted to mention. And if these clips play, I just wanted to show quickly, how stiff these mixtures were. This is the first load that came out. As you can see, it's almost like dry gravel right there, right? And look at this inspector. He's not really happy about it. It was very, very dry. And then looking at the edge there, and when they were finishing it, a lot of these edges really fell apart, and then they had to refinish the edges after the fact. And then so far, I think after the year 1, even now, they've been holding up. It would be interesting to see how it holds up after 2 or 3 years. But then I should mention that the original plan was to pave 228 feet of this particular test section. They did try to get 70 feet, but then we had issues with the mix being too stiff, so they stopped paving. And then right now we only have 15 feet of this material left. 2 slabs. The 2 slabs are still there, no repairs performed except grinding, but they are still there. We'll see how it goes. All right, the next material was the Astro blended cement, and similar to the ultra high materials, the initial batches were relatively dry, but then with subsequent deliveries it did improve. But one issue we had was with a lot of these, not just on this project, but the carbon dioxide and the alternative pozzolanic project, the delay between in getting the subsequent mixes, right, up to 45 to 1 hour wait time in getting the trucks from the batch plant to the site. That was also a big issue with a lot of these mixtures. And we did notice that this mixture was not blended very well. Probably an artifact of the super sack issue, and the material received from the manufacturer was not enough to finish the 240-foot test cell. So we had to backfill it with the control section, and the entire test cell was diamond ground for this particular cell, except over the panels with the sensors. And the next cell, 20 to 16 TerraCO2, again super sacks, and not many issues with this mix, except once 75% of the paving was completed, we did see some of the edges that were falling apart. They had to be, they did collapse, and then they had to be readjusted and finished after the fact. And then this test cell was also diamond ground completely, except all the cells with the sensors. And the study control, you would not expect to see any issues with this particular mixture. That has been using it routinely. And one issue that was noted was in localized areas, we did see some excessive bleeding, and then we had to wait about 1.5 hours for all the bleed water to be sucked in or evaporate. And then only then the curing compound is applied. That was the only real issue was with this particular with the control mixture. And the continental cement, again, this was based on what Larry said. He was there for this particular. He did not note anything on his field sheet. I meant that to say that his mixture had no issues. Slump seemed to be acceptable, mix was placed properly, and this cell was not completely done underground. I think they left some cells underground just to see how the drivers maybe behave to that slick surface. But anyway, some panels were diamond ground, and you can see the difference in texture before grinding and after grinding. And if you folks are there at the MnDOT site after the meeting today, you will get to probably see a lot of these test cells. And in general, the one main issue with the constructability was a lot of these materials came in huge super sacks, and they take a lot of time in getting these transported pneumatic tankers, right? And then it presents potentially a hazardous environment for the workers, and also you could waste a lot of material with spills. And then a lot of these mixtures did have blending issues. I did have to note that. And finishing issues behind the paver and dry mixtures, we had to remove and replace them. And then there were some self-collapsing edges that had to be restrained manually and refinished at the end. And as we noted earlier, several cells had to be diamond ground to attain the desired texture. And we did go out there to look at these test cells last year, year one performance. And one thing that we saw in all the test cells was, about 12 inches from the outer shoulder, very, very minor spalling. Almost every single slab had that. We have a drone video showing that. And since every single test cell had it, not just this project, but all the 3 projects, it was probably something to do with maybe irregular panel elevations. We thought that, but we did put a straight edge. We did not see anything out of whack there. It seemed to be okay. And then maybe snow plowing issues contributed to it. And then we also hypothesized that it could also have been due to an irregular vibrator at a paver, but we don't know what the exact reason is, but we did see a lot of low severity falling through the entire length of almost every single slab there. And ultra heavy materials, like I said, only 15 foot left. You might miss it. You have to carefully observe for this test cell while you're out there on your field visit today. Only 2 slabs. And then again, it is there. No repairs have been performed since construction. The 2 slabs remain to this day, I believe. Ragged joints, possibly due to the dry nature of the mix, and some areas of localized pop-outs and joint spalling. And then the Asbro blended cement, again, the recurring spalling that we saw throughout the length of all the test cells was less pronounced in this particular cell. But then there was a large full depth repair. I believe that was because of a transverse crack that was near the middle of the test cell. And then we also saw some localized areas of shrinkage cracking. And 2216 terrace CO2, same thing, transverse joints. In a lot of the transverse joints, we see some low severity transverse faults. And then there were some isolated areas of pop-outs. Other than that, no cracking, no shrinkage issues, seems to be doing pretty well after year 1. Study control, you wouldn't expect to see anything. And this cell was not diamond ground. You do see the turf track texture right there. And then we did notice that the first 4 or 5 joints were skewed, maybe at a 10-degree angle. I don't know whether this was because it was done to intentionally mask double basket orientation, or it was just the paving, the sawing crew just wanted to have some fun out there. I don't know what the issue is. But anyway, we did notice that the first 4 or 5 joints were skewed. And then continental cement, again, we did see some isolated pop-outs and one small task probably to repair, or I think this was to repair a misaligned tie bar. Yeah, there was a misaligned tie bar at this particular location. And then we did see one small patch there. But other than that, no cracking, isolated pop-out areas, and seems to be doing pretty well after year 1. And then I'm not going to show you all the test results, and going to show you some testing that was performed after construction. These are some roughness numbers, right quality numbers. Looking at the IRI values, you should take this with a grain of salt. These are 200 feet sections, right? And we are not wanting to focus on the absolute values. What we are more interested in is how these trend over time. What happens to these test cells over time? And again, like I said, these are short test cells, but looking at the IRA numbers, most of them fall between the 600 to the 100 range, generally offering pretty reasonable ride quality. Obviously, most of these test cells were hand grown. And surface friction values, again, no issues there. Most of them, the rib tire and the smooth tire testing was performed. And you see most of these values hovering around the 60 range for the rib tire and the 40 to 50 range for the smooth tires. Again, like I said, we are more interested in looking at how these trend over time rather than the absolute values here. And load transfer efficiency was also performed, and most of them are in the 70, 80, 85 range. The testing was performed, the load before the joint and after the joint also, and there are some other additional statistics we did report in the report. I think that is published on the NRRA webpage. You can take a look at that. And then in addition to this testing, MnDOT did include a lot of embedded sensors. We have a lot of data coming in. I'm not going to show all that today, but probably in the next meeting or the meeting after that, once we have data from years 1, 2, and 3, we can look at trends over time and maybe show you some observations from those sensors. And year 1, what did we see? No significant signs of premature distress. Right after year 1, most of these testers are still there. Some isolated areas of pop-outs, a little bit of shrinkage cracking on a few panels, maybe some one full depth repair on one particular test cells, one small patch. Other than that, no major tracking issues. Seems to be doing pretty well. Ride quality is good. Friction numbers are in the expected range. And then there was some limited petrographic analysis performed by AET. And then most of the cores seemed to be in good condition. There were no signs of freeze-thaw damage or no ASR damage. But one thing they did note was they did see carbonation at depths that exceed typical expectations for 1 year. 1 year after construction, you would expect maybe 1 millimeter of carbonation, but they didn't see carbonation at depths even like 6 to 7 millimeters. Maybe due to diamond grinding, I don't know, maybe due to other issues inherent with inherent nature of these mixtures. But again, only one core was tested. We should take the results with a grain of salt, but really, nothing to say that these mixtures have any durability concerns. So in terms of next steps, we will be doing a year 2 monitoring this year, possibly combine that with the ISCP conference. I think the Thursday is reserved for the field inspections. We are looking to combine our field inspection, our site visit along with that. And then we are also working on task 7, which is the sustainability evaluation. We did survey the material producers as a part of the study. What we wanted to get was, have they done any environmental analysis? Have they conducted a life cycle assessment? Do they have an environmental product declaration for their mixtures, or are they planning to develop an APD for the mixture? Really, some of them have done some life cycle assessment studies. They do have information on global warming potential for these mixtures. That is the type of information that we are trying to obtain. And then some of them they said they are in the process of developing EPDs for their mixtures. And then we've also developed a system boundaries for life cycle assessment for these particular test cells that we are evaluating as a part of this project. So we can look at material manufacture, transport to the plant, and then plant to site. We're going to look at a simplified environmental impact analysis. And then we are planning to reach out to the producers again to develop more informed assumptions for the life cycle assessments that will be conducted as a part of the study. And that's it. And with that, I leave you with a poem my daughter wrote last week on climate change. And that's all. I'm happy to take any questions. Thank you.
Basically, what is like the ultra high strength material is composed of? Like, is it a proprietary or any?
Yes, it is a proprietary material. It could be modification of CSA cement, calcium sulfur made, but don't know that for sure. That information, I think maybe a few people have it. Larry knows it. Maybe if you pay him some money, he might help.
Would you like to comment on why we're starting to present 56-day testing results?
So, yeah, I think typically we've been reporting 7-day, 14, 28, right? And I think there is a shift to the 56 days, and I think that really is what is needed to give you what you would expect to see from the performance standpoint. We really need the 56 days trend. 28 days trend is not really reflective of what is happening out there. So I think the standards are probably going to change in the future to require 56 days versus the 28 day or even 7 days. So that's maybe has MnDOT made a change in their spec stuff.
No.
I have.
Not yet. All right.
What's the reason? Slower development of strip?
Yeah.
Ultimately.
For this particular mixes, you see a slower development of strength clean, and they do gain strength even after the 28 days. And if you see, especially for some of these mixtures with the manufactured fly ash from 28 to 56, there is a big jump. You do have to wait till the 56 day to get your requirement. And I think for opening the traffic, what is MnDOT's requirement? Is it 3,000 or 2,000? That was changed from 3,000 reflection to 2,000, right? Recently. And again, strength is one parameter. Strength is not the most important parameter. That's another thing to keep in mind. Any other questions?
With the issue of the super stacks, do you think if you scaled up the project and got out of the main road, that the delivery method would change and that issue would resolve itself?
It could. It's possible. I'm not sure. It clearly depends on how they were the producers were shipping out for this particular project. But yeah, you're right. It could change.
For this year, we are not allowed to do the super stack. We don't want to deal with it. So they are going to have to put it into a chamber. So, that answered your question. Yes, we want it like it would be in high production.
A very nice presentation. I just a suggestion. I don't know if you consider, but we did IC mapping on the passing lane. Soil came and for some of these cells. So I'm curious to see maybe some of these unexpected distress that you see, the spalling and the weird spots are related to anything with the foundation. It would be nice if we can look at the data and see if we can inform or explain some of these unexpected trends. So
I don't believe it would have any issue with the foundation. I think it's just a very surface thing. It seems to be an artifact of construction or snow. We don't know exactly what it is, but I personally do not believe it has anything to do with foundation. But yeah, like you said, there's a lot of additional data. I think they did on the load document they collected. I don't know if there is a plan to do NRRA or other testing, looking at down alignments and things like that. But any additional information that we see from MnDOT, we will include it as a part of the hearings and the final report. Thank you. Any other questions? Oh, one more. None.
I need to add to clarify what Dr. Velasquez was just asking. You know, it's good, use the PIs. Always include in your report the fact that the base is not a confounding factor. Yes, you think it is. You know, the reason is that we did a lot of due diligence, especially due diligence to ensure that the base is not confounding. I think that's the point we need to emphasize.
Thank you, Burnham. Any other questions? All right, thank you.
Good morning, Joel Allring here again with the PM team or preventative maintenance. I'm going to briefly talk about the 3 projects that we're currently working on through the 2023 call for innovation. We did approve 3 additional projects. The hot rubber seal coating. That's project is to demonstrate the use of hot rubber seal coating to reduce early onset of stripping and extended pavement life. It's going to consist of both lab and field demonstrations. The PI is Zamping Yu out of Michigan Tech, and the TL is Joseph Podolsky out of MnDOT. The second project is materials-based methods to improve rumble strike durability, co-sponsored with the Flex team. And that's to investigate the impact of Hoegh reducing asphalt membrane, or VRAM, and rapid penetrating emulsion, RPE. What they have on the, I guess, can't read my own writing here. But the rapid penetrating emulsion, what they have on the centerline rumble strip and the durability of that. The PI on that is Dan Schwartz. He's with Asphalt Materials Inc. And he's assisted with Katie Carlo out of Heritage Research Group and Signe Reichelt out of Benke Materials Engineering. The TL on that is Tyler Hunt, Michigan Tech, or excuse me, Michigan DOT. And then the third project is the use of recycled materials in pavement, preservation treatments. They want to evaluate the feasibility of using recycled materials in chip seals, slurry surfacing and microsurfacing treatments. That's to include also the economic and environmental benefits. The PI on that is Adriana Vargas out of NCAT and Fabricio Leva, excuse me if I slaughter these names, but out of Clemson University. And the TL on that is Emil Batista of MnDOT. Next, I guess I'm going to introduce Raquel. Raquel Moraz is out of NCAT, and she's going to talk to us today about her lab testing on the spray applied rejuvenators. So Raquel.
Good morning. So today I'll be presenting the findings of the study of an analysis of the long-term field performance of spray-on rejuvenators. First, I'd like to acknowledge the research team, myself, Dr. Fanny, and Nathan Moore from NCAT. A little bit of the background on this study. We know that the binder near the pavement surface with time due to the oxidative aging become harder and therefore more susceptible to distresses caused by oxidation, which can be reversed when we apply treatments that we are called as spray-on rejuvenators. There basically are rejuvenator products that can apply by itself or in conjunction with asphalt emulsions or other products such as polymers to renew the surface of asphalt pavements. The overall motivation for this study is related to the fact that there is a lack of information regarding the composition of these products and also how these products behave after a long term of application in the field. And there is also an important safety concern related to these treatments because these treatments can decrease the friction and the skid resistance of the pavement. Currently, there is not a specification that we can be used to classify or to select these treatments. The most used specification is the FAA procedure P632. But there is some concerns related to this specification, especially related to the fact that this specification classified products considering a short time of window after application in the field, between 30 to 45 days after the products being applied. Another point of importance from this specification, considering the performance of these products, is related to friction characteristics. There is also monitored considering the P632 procedure. So with trying to answer some of the lacking of information related to these treatments, this study was developed And the overall objective of the study is to evaluate the field performance of 12 products that are available in the market, considering the short and long-term performance of this treatment, and also how these treatments can affect the pavement friction and reflectivity. 2 researchers contracts are ongoing related to this study. One between the NRRA and Auburn University, where we are focusing on the evaluation on section construct at main road, and another one sponsored by the LRRB that is being performed by Michigan State University, focusing on field characteristics of a San Michael road and main road sections. Here you have a picture of the project location at the main road, low volume road. We have 2 surface mixtures that are constructed in 2021, containing 20% of RAP. The basic difference between these 2 mixtures is the asphalt binder used on it. One has a PG58S-28 binder, and another surface has a polymorphied binder, PG58H-34. On each of the surfaces, we have 12 products being applied. Here you have a list of the products used in this experiment. You can see that they can be divided in 3 major categories. One that is the bio-based products, another one that classified as a hybrid combination between bio and petroleum-based components, and the third are the petroleum-based products. You can see that among the 12 products, we have 5 that has polymer in their composition. You can see on the third column here the residual application rate of these products. We have to emphasize that all the properties for application of these treatments, considering the residual application rate, the residual of oils, they're all indicated by the manufacturers. And for discussion of the results, I'm not going to be giving names to the products, but these products will be random labeled between product 1 and 12. The work plan is basically divided in 3 major steps. The first one is the field evaluation, where we monitor friction, reflectivity, macro and microtexture, and also collect field cores for binder evaluation. For extraction of the binders from the field cores, we are aware that the solvent using the process can interact with the treatments that we are using. So therefore, we ask for the producers what would be the most appropriate solvent for extraction and recovery of their product. And here you see that 3 of them requested a blend of toluene and ethanol, and the majority of the producers required trichloroethylene. And the control binders are also extracted and recovered using trichloroethylene. For binder evaluation, we performed the test that you can see here listed, basically DSR and BBR testing. You can see, as mentioned before, that the current specification for cost, if we can call that, used for evaluating these products is the P632. On the P632, there are 3 major parameters that are accounted regarding the binder rheological response. And to not only look into these 3 parameters, we add other testings for evaluation of the extracted binders. And last, the third step of this study is the chemical evaluation of the treated asphalt binders, where we are performing FTIR to evaluate oxidative products, and also the SARA fractions to see how these treatments can change the chemical fractions of the asphalt binders. I'm going to now start to discuss the results. For today's presentation, due to the limit of time, I'm going to be focusing only on the rheological response of the binders and some results for the chemical analysis. I will not be covering the field data for this study because the team from Dr. Curt from Michigan State, they have been presenting that, and because of the time, I cannot cover everything. Also, before initiate to discussion of the results, I just would like to highlight that neither NCAT or MnDOT have no interest on any of the products that are evaluated in this study. So no bias here on any of the results that are presented. And second, and most important, all the binder data to be presented here are originated from extracted binders, extracted and recovered binders. So I want you to consider that we know that because of the solvents used in the treatment, we can have interference in the response of the data. True, so, but it's very hard to account for that, but we have to keep that in mind. So the first set of data presented here is related to the surface with a neat binder PG58S-22. And here you can see the passive fail temperature at high end of the performance rating. You will see divided control, bio-based products, the hybrid product, and the petroleum-based products. And we have results after 1 month, 12, and 24 months of treatment being applied. For each section or category of products, we have the data organized from the lowest passive temperature to the highest, considering the 1 month field age interval. It can be seen that regardless of the category of the products being evaluated, we see a significant decrease for some products regarding the passive fail temperature at the high end of the PG after 1 month of treatment application. You can see that, however, not what was observed after 1 month of the treatments being applied is what remains after 24 months of these treatments being placed in the field. So, and when considering the bio-based and the petroleum-based, you can see that the petroleum-based products resulted in much lower passive fail temperature compared to the bio-based product, regardless of the field age interval. For the lower end of the PG, we see similar trends, where we can see a significant softening for some of the products. After 1 month of treatment application, as aging progresses, this decrease starts to be minimized. However, we also see for some products, and this is more emphasized for the surface that contain the polymeric material, that some of the products needs more time than the short window of 1 month to really give the full response in changing the rheology of the binders. Here we have results for the delta TC, where we can be evaluating the cracking potential of the asphalt binders. You can see that by the results of the binder itself, the section has a very good binder, and because the pavement was brand new, the delta TC after 1 month for the control binder was 0, which is considered very good. And so any the placement of this treatment would be additional improvement for the binder. And you can see that regarding the bio-base and the petroleum base, the petroleum base, as we saw for the low temperature PG and high temperature PG, resulted in the biggest improvement per se in terms of delta TC for the neat binder section. Here we have the results for the polymeric surface that contain a PG58H minus 34. We see similar trends that were observed for the PG58S minus 28. However, an interesting finding can be seen here, especially for this polymeric surface. We can capture that some of the products really start to have like a peak of action in a longer time after application compared to the neat pavement surface. Where you can see, for example, product 6, product 4, product 9, you see that they really impact in softening the asphalt binder was captured after 12 months of field application. And this can also be seen here when we consider the low temperature performance of the treated sections. You can see for several of the products that the timing of interaction between these products and the asphalt body in the surface of the pavement was higher or longer compared to what was required for the neat binder. In terms of delta TC, as observed for the PGS binder, we can see that the petroleum-based additives are the ones that give the best improvement on it. So, trying to summarize what was presented in terms of the effects of the treatments in the delta TC of the binders, a ranking was established, just for us to try to see if what was captured can facilitate us when ranking categories of products and it effects on reducing the cracking potential of binders. So you can see here the difference between the delta TC of the treated sections and control sections after 24 months of being applied to the field. And for the first set of data is related to the surface with a PG58S-28 binder, where the second one is the polymeric binder 58H-34. You can see by the color coding that for the 58S-28, the products that are more effective in improving the delta TC of the control binders were the petroleum-based one. And for the polymeric base, we had a mix between the first, the best products being petroleum-based and bio-based. Same ranking was established considering the effect of the products on the low temperature PG of the binder. We know that delta TC has a meaning only when we are considering the stiffness of the binder reaching 300 megapascal. So we have also to consider the effects of these treatments in the low temperature PG. So we can see here that the ranking again is different if we consider the neat binder and the polymeric binder. And for the neat binder, again, the polymeric or the petroleum-based one are the ones that are giving the best response. We also evaluated the multiple stress creeping recovery response of the binders. Here in the slides, you have data for the neat pavement surface with the binder PG58S-28. The same trend that was observed, considering the high temperature PG, can be captured here, where you can see that overall, for some of the treatments, we see a significant decrease on the stiffness of the binder. And as time progresses, that binder ages and that the stiffness starts to increase. Important factor is like for some of the treatments, we have a change on the traffic rating after 1 month and 12 months of treatments being applied. But as we reach the 24 months, the same traffic rating for the treated sections was exactly the same as the control. Same response observed for the PG58H-34 binder. Again, specifically for this binder that contains a polymer, we see that the maximum solvency of these products was not captured at 1 month, but later on after we reached 12 months of treatment application. Regarding the parameter used by the P632 specification, we have stiffness at 60 Celsius degrees and 10 radians per second. Per the FAA specification, if a pavement is less or equal to 3 years old, for a product to be classified as effective, this stiffness needs to have a decrease of equal or higher to 25% between the time interval of 30 and 45 days after the product's being applied. You can see here on this graph, what is indicated on red means that we see a decrease in the stiffness of the treated binder compared to the control section. And what is in red shows that instead of a decrease, we saw an increase. And when considering the gray columns that are the data after 1 month of treatment being applied, we can see that some of the products that are marked with X did not reach this requirement of the P632 procedure, meaning that if we are supposed to classify these products, considering the specification, they would be rejected because they do not decrease the stiffness of the binder at the specific window of 30 to 45 days. However, for some of the products, like for example, product 6 and product 3, we saw that over time, they would pass that criteria of the P632 procedure, while, for example, product 7 and product 8 would not. Same evaluation was performed for considering now the polymeric asphalt surface of having a PG binder 58 H minus 34. On that specific treatment, as we saw from the previous data presented, these treatments did not reach its peak on effectiveness after 1 month of application, but rather later on. So we would discriminate much more or eliminate much more treatments considering the polymeric asphalt surface, right? As we were considering the PG 58S minus 28. The data presented on the previous slides is now summarized here in these two graphs. You can see on the left side, the treated surface or bio-based product, considering the control PG 58S minus 28. And on the right side, the same product, the bio-based product, considering the PG 58H minus 34 binder. You can see that first, there is a significant difference on how these products are responding for the need binder and the modified binder. We can also see that for considering specifically the PG58S minus 28 binders, that even though we have a significant decrease in stiffness after 1 month of application, as time progresses, these treatments start to be differentiated and not necessarily the treatment that has the highest softening after 1 month of application is the one that remains having the lowest stiffness after 24 months of field aging. Same comparison now considering the petroleum-based products, where on the left side graph, we have results considering the PG58S minus 28 binder, and on the right side, the PG58H minus 34. Again, we see that the response of these products differ based on the binder present on the surface of the pavement, and that what is captured after 1 month is not really the actual response on the long-term performance of these treatments. Another way that we try to evaluate if these products are being effective or not on decreasing the stiffness and enrichment of the base binder was using the Glover-Rowe parameter. So here, for this, we have created a Glover-Rowe effectiveness index where we use the Glover-Rowe parameter of the treated binder from field cores collected after 24 months of field aging, and divided by the calculated Glover-Rowe parameter of the control binder also after 24 months of field aging. So basically, we want to see the effectiveness of these additives on really changing the enrichment and stiffness of the binder. So we want these results to be lower than 1. So that would mean that these treatments are really working against the stiffness and enrichment of the binder. As you can see here, some of the bio-based products would pass this criteria considering the Glover-Rowe parameter, and while the petroleum-based products would all be classified as effective. Same evaluation now, considering the PG binder 58H minus 34. Here we can see that overall, the bio-based products, if we consider this parameter, would be not so effective on reducing stiffness and wrinkling the binder, while again, the petroleum-based ones would be more favorable. Regarding the chemical evaluation of the treatments, as mentioned before, we did the separation of the 4 asphalt fractions. And with that asphalt, that's fractions, we calculate the colloidal instability index. Basically, we wanted to see the components that must be dispersed divided by the dispersing components of the binder. And we wanted this colloidal instability index to decrease. So it means that our asphalt binder is more stable. You can see here that in comparison to the control, we see the majority of the products regarding of if they are bio-based, petroleum-based, or hybrid, they seem to decrease the colloidal instability index of the binder after 1 month of treatment application. And here's results for the PG 58H minus 34 binder, where we can clearly capture the effectiveness of these products, considering the colloidal stability of the binder. One thing that I need to mention is that we use solvent to separate the sour fractions. And because these bio-based and petroleum-based treatments, they have components that have high polarity. They could be attached to the asphaltenes that are present on the binder, and therefore, on the first step of separation for the sour fractions, they would be washed out with the bad components. That would be the asphaltenes. So sometimes we have to look to these results with caution because they can be misleading. The other chemical evaluation performed for this study was FTIR to evaluate the carbonyl and sulfoxide areas. Because it's known that if a binder is said to experience aging, that binder would have a higher area of carbonyl plus sulfoxides compared to a binder that was less aged. It is known that these products, especially the bio-based ones, they have fat acids that contains carbonyl groups that if they are not counted corrected, they could indicate these products as being ineffective in terms of oxidative products when considering FTIR evaluation. Therefore, what was done here, we use an approach where only the carbonyl that are attributed to the fat acids were considering the calculation. So the benzylic bad carbonyls were not accounted on this. So you can see that with this approach, we can capture that all of the products are reducing the aging of the binder between 1 month and 12 months of field application. Same evaluation performed here for the PG binder 58H minus 34, and we can see the same trend. Key takeaways of the study. The database that we are creating for this study is very large. You can see for each of the tests that is performed in this study, we have 84 samples being evaluated when considering the 2 surfaces, the neat binder and the polymeric binder, the 12 products applying on each of the surfaces, and the 3 field aging conditions. So the database is huge and is being used to feed an NCRRA study that is being performed right now to establish specifications for classifications and acceptance of these products. From the data collected in this study so far, we see a decrease in the continuous rate of the extracted binders at high temperatures and low, indicating the softening of the treated sections. We see also that this treatments improve the cracking resistance as indicated by the delta TC, even though after 24 months of being applied. There a longer period was required for some treatments to achieve a maximum performance, especially when considering the surface containing the polymeric asphalt binder. So therefore, the window of 30 to 45 days after the treatments being applied can be misleading. And the chemical analysis performed so far has indicated the benefits of these treatments. This project has not been finalized. We are finalizing the field collection, the data collection after 24 months of treatments being applied. We still have to finalize the chemical analysis after 24 months. We have presented 1 and 12 months only. So we still have work to do and to combine all of this with the field data collected, especially fracture response of these treatments. We'd like to say thank you to the Minnesota Department of Transportation for sponsoring this study. And also to say thank you to Michael Curtis for all the help and support. And if you have any questions, please let me know.
Question, Michelle? Thank you.
One question, a comment. I hope that after timing and all arguments back when we were applied there, that after the NMS won the World Cup, now that you agree with me that Argentina soccer is better than Brazilian soccer, right? And the technical question, with all your experience, all your strong background in chemistry, all the work you have gone through all the years, do you see that eventually we'll be able to connect the chemistry of the binder with the SAR, IPR, with rheological performance, or do you feel like way too much to go?
No, for some, it's a great question. It's a great question, and we see when we lead with the binder by itself, the neat binder, that correlation is much easier than when we have these additives. Because if we rely, for example, in analytical testing that has solvents involved, we can have these components interacting with the solvents, so it makes everything more complicated. But we are working very hard on established patterns between products and binders and agents. So yes, the whole goal of using these two is to try to see that, like, where the chemists explain what we are seeing. And also, like, we do not have hopes that all departments of transportation will be having to be using analytical tools for evaluation. So we try to see if the response that we capture from the chemistry can be related somehow with the rheology, so we can replace a chemical analysis by the rheology.
Any other questions?
You gonna let him get away with the first comment?
I guess so. Thank you.
All right, thank you.
Right now, Lauren is dealing with communications related to food, so I will skip over that and kind of just summarize kind of what we did the last couple of days. You know, it was really interesting to talk about the implementation, and I kind of get a kick out of it, but you know, you sometimes look at the implementation, you say, well, we haven't gone very far. You know, you can say that kind of things, but look back 5 years. Some of you can look back 10 years. Some of you guys can look back a lot more than that. I mean, think of the stuff that we're doing way back when and where we're at now, it's huge. I mean, we're doing things so much smarter, so much easier, so much cheaper. Things have really improved. And then today's talks related to some of the work that's going on, it's really encouraging seeing what the current work is going on and where we're going with that. So all the speakers did a great job and I really appreciate it. The chairs have done a wonderful job. And I'm gonna kind of go through this. I'll pretend I'm Lauren if that works at all. But again, I also kind of wanted to talk about, you know, we also are kind of challenging the norms, which I think is huge. We've really challenged those, and that challenge really has kind of developed into this new way of doing things. I mean, that's where we're gonna succeed as a industry, is moving towards that. You know, and again, you've seen a lot of interesting stuff too related to some of the sensors and how we're monitoring things and how things are going. It's just gotten a lot more technical, a lot more ability to use that technology to advance what we're doing. So with that, I was gonna let Lauren talk a little bit at the time.
All right, thank you. I just wanted to cover a few outreach opportunities that we have that we focus on for NRRA. And the first one is through our monthly activities, through the each of the team meetings and our webinar series called Research Pays Off. We are certainly open to additional ideas, always looking for more topics for Research Pays Off. I apologize, I should have looked through these a little more closely before I got up here. Then yearly we attend a few different events around the country. We've got TRB. We have previously done some booths there, but really want to focus on allowing all of you as members to network and talk with other people rather than having to spend time standing at a booth. And then we've got obviously this meeting here. And then this year we have a couple other focused events that we're going to be attending as well for concrete and IC. And then on our website, everything that our teams do is all tracked on the websites, and for each of the projects, we've got project pages for each of those. And then in the future, we would love to make sure that our team meetings are as effective as possible for tech transfer and just keeping people in the loop. I know they're not always at times when everyone can attend them every month, so that just is what it is. But if you have any other ideas about how the team meetings could be shaped or other things that we could do to help get the word out about NRRA, please contact myself, contact Ben, talk to your department or your team chair, talk to the executive committee. We always want to be improving, and there's always opportunities for growth in those areas. And just a reminder that LinkedIn is kind of our primary external, besides our website, LinkedIn is really our primary external resource and hub for getting information out. So this is a reminder that if you don't follow our LinkedIn page, to do so and share the posts that we make about Research Pays Off and events like this, because that would be helpful. One other quick thing I wanted to do is just take a group photo while I'm standing up here. So let me just set up my camera here and try to get the whole room over there in the shot. You're all going to be really nice and tiny. Tom, you're the only person I can't see, I think. Yeah. There we go. All right. 1, 2, 3. Great. All right, Ben.
All right, thanks, Lauren. Let's see where we're at with this. Again, I kind of talked a little bit about the history and, you know, kind of where we're at right now. We're moving now into our, you know, we've gone through phase 1, phase 2. We're right now into that. We got 2 more years of phase 2, but it's time to start thinking about what we want to do for phase 3. So start thinking along those lines and where this is gonna go. It seems like we got really good momentum for myself. But again, we need to start talking about what we want to do coming up in the future. Again, this is a pooled fund, so there's a lot to be said with that, but some of the details related to the pooled fund, you can go to the pooled fund website, you can see quarterly reports and stuff that we're doing. But again, the NRRA website is the best thing that Lauren's kind of put together for that. And again, thanks to Steve Cooper for being a part of this. Really appreciate your efforts and supporting not only NRRA, but all the technologies that we're developing as a group. Executive committee, again, we met just a little while ago in April, and we talked. We also have the technical chairs that are part of that to keep them, on the same page as everyone else that's going with it. But we did fund a couple different things just recently, just for your to know about. The ICT meeting in Florida, a lot of stuff with Amanda was talking about earlier. There'll be we'll be sponsoring travel to there, along with the concrete consortium. So the state DOTs that are part of NRRA, you have two opportunities. So you can either attend both the concrete or one or the other. So you got two trips. So pick which conference you want to go to and kind of go with that. Does that make sense? All right. So this way we're not saying you got to do this or got to do that. It's your choice to do what you want. The other thing too is we had the Wicking Geotextile. Talked a little bit about in the Geotech group. That one's got an extension on it. So hopefully we get a winter this year and they can see what happens. That happens with that. And also we kind of looked at what kind of money we had available, and thought I put this on the slide, but really we're looking at holding off till 2020, later on in July to kind of figure out what we want to do the rest of our funds that we have. Bear with me 1 second. I'm going to go up, go down. All right, I guess I'll go. So I guess when I talk about the rest of the funds, so we have some flexibility in what we want to do this summer. We want to get things contracted fairly quick, just so we can kind of get it in phase 2. But we're kind of seeing what kind of this conference brings about, see what the teams kind of talk about it in a couple months here up till July. But again, the executive team really looked at MnROAD construction. They were wanting support. We were kind of talking about that. We have funds that we can use on our interstate road, but we can't use it on the low volume road. So when we want to start incorporating maybe some test sections there, we really could utilize that. So the executive committee was in favor of that. We just didn't put a dollar value to it right now. Again, they really wanted the idea of implementation. How can we foster that? How can we put dollars towards that and move forward? And again, we're looking for the teams up, input on some other things too. I mean, Raquel talked a lot about her aging testing. Maybe we need to go farther into that for more years. Lots of different things that we could maybe look at. So again, I want to do the thank yous, a couple different things. All the NRRA members, the associates, the agencies. I also wanted to say, a lot of great work is being done at MnROAD. You'll see some of those people that aren't necessarily in front of the microphone here, but they're doing all the hard work. They're the ones that are doing really interesting things with sensors, really going out there and measuring stuff when it's cold and windy and rainy. So thank those people out there. They do the great work, getting you the data that supports a lot of these research efforts. And I guess real quickly, Joel and Rebecca, can you please come up? Where's Joel? There he is. And where's Rebecca? There's Rebecca. Rebecca's a little slow, so I'll start with Joel. Joel, I wanted to say thank you very much for your chairing the PM team, and I really appreciate your efforts with that. So thank you, Joel. And my friend Rebecca. It's always fun to say Rebecca. So Rebecca, again, thanks for chairing the ICT team. Curt did a great job with that. Really appreciate it. So thank you. I learned not to have the microphone in the picture, the second one. But again, also Ollie was part of the Rigid team, that's part of that, and he's not here today, so I don't have it. So the last one I would like to say is our friend Jeff Brunner, who's been really supportive of all the research and all the crazy things. Jeff, you kind of see Jeff's background there. I had to figure out a way. Jeff's always had this little picture of his face on the sign-in board someone put on there many years ago. So I took a picture of that, and I got this magazine from an ITS thing, and I threw that in there and put Jeff in a car. But again, Jeff's not like all of us. He drives on the other side of the road and things like that. But he's been a wonderful person in all the efforts he's done for me personally and for our whole team.